Hello and welcome to the 2021 Display Week program. We are happy you have joined us for this short course on fundamentals of display metrology. This course will include approximately 4 hours of educational material with topics led by representatives of our three companies, Instrument Systems, Konica Minolta and Radiant Vision Systems. Cumulatively, the presenting companies bring over 100 years of display metrology research and innovation to the field of measurement. This course will condense knowledge from our teams and provide you with an excellent framework for understanding metrology and the latest display test advances. Given the virtual format of the presentation, we welcome you to review the course at your own pace. Should you have any questions, send us a message using the QA so we can get in contact with you. Let's get started. Our course agenda has 4 primary sections. First, measurement principles, which introduces the science of metrology. Second, measurement equipment and calibration, which describes the tools used for a range of display metrology applications. Third, measuring specific display characteristics, which explains how visual qualities of displays are captured and quantified. And fourth, addressing emerging display types and integration, which introduces some of the latest display metrology tools and methods. Our presenters today include myself, Reto Häring from Instrument Systems, as well as my colleagues Yutaka Maeda from Konica Minolta and Jensen from Radiant Vision. Let me introduce myself. My name is Reto. I have joined Instrument Systems 2010. Several years I was heading the R&D department and was head of laboratory and metrology. In 3 years I am working closer to customers. Currently I'm heading the department Customer Solutions, dedicated to understand customer problems and find the right solutions. I'm looking forward to show you today the fundamentals of display metrology, but also going into the current challenges in industry.
Hello everyone, my name is Yutaka. Let me start my introduction. I joined Konica Minolta in 2013 and started my career as an engineer. After involved in new product development, I took on a role in application engineering and business development to implement display measurement solutions for the company's major customers. I'm really looking forward to making this presentation today. See you soon.
Good morning. My name is Jensen. I am the Vice President of Product Development at Radiant Vision Systems. I've spent 11 years in the company developing camera systems, lenses, and other equipment used for display measurement. Before that, I was 23 years at the Danish Photometry and Colorimetric Laboratory in Denmark. I have a master's degree in mechanical engineering from the Technical University of Denmark. We will start this presentation with an introduction to measurement principles. This first section will introduce the science of light and color, displays, and units of measurements, which are fundamental to metrology. Display metrology is about quantifying the visual output of a display. The display output is light, which determines the visual qualities of the display, including brightness, color, contrast, and much more. This section is a review of the science of light and color and the methods universally accepted to quantify these properties. Light is electromagnetic radiation described by the direction, orientation, amplitude, and wavelength. The entire spectrum of electromagnetic radiation spans from the very energetic short wavelength gamma rays to low energy long wavelength radio waves. Radiometry is the science of measuring radiation in the entire spectrum. By choosing a specific measurement setup, radiometric measurement can quantify wavelength, power, intensity, reflectance, etc. In every setup, there is a device collecting the radiation by converting photons into electrons. Our measurements are counts of electrons, proportional to incoming photons, proportional to the radiation. When we measure, we are just counting photons. The rest of this short course will only be about light, the visible part of the full spectrum of radiation. Light is the spectrum of radiation that can be detected by our eyes and interpreted by our brains. This spectrum roughly lies between 380 nanometers and 700 nanometers. The unique way we perceive these wavelengths based on the response of our visual system provides what our brains understand as brightness and color. The visible spectrum of light is human-centric. The human perception of color is, for instance, different from that of a honeybee. The human eye has evolved to be, for our purpose, uniquely sensitive to sun and daylight, which yields our perception of the world. Our measurement devices and metrology allows us to measure hard quantities of a display. What is the luminance of white and black yielding contrast? The luminance distribution yielding the uniformity, how large is the color gamut, etc. But we cannot directly measure the human perception of the display quality. We do not have a perceived quality-o-meter. From studies or experience with the human vision system, we know that knowledge of a certain number of measurable properties will allow us to, with some degree of accuracy, quantify the perceived display quality. Behind the specification sheet of a display are a vast number of measurements. After various mathematical operations, the marketing department can fill out the specification sheet with properties that would help the consumer to understand the display quality. But in the end, the consumer will probably want to see and compare the different displays before making a choice. Later in this short course, the units used to describe or quantify light will be explained by Dr. Häring. For now, let's use some common language to get an idea of light properties important for displays. The light from a light source can be spectrally characterized by performing a spectral radiometer measurement, which reports the power distribution of the emitted light as a function of wavelength. Some light sources emit light only in the visible range, while other sources can emit part of the light in the UV, ultraviolet region, or in the infrared region. Most colored LEDs and most display primaries falls in the first group, and those sources will only emit light in a narrow range. Daylight and incandescent lamps are examples from the second group. Common for what we refer to as light sources is they emit some radiation in the visible region of the spectrum. In the shown graph, the spectral power distribution, also called MSPD, for various sources are shown. If a spot is illuminated by a mixture of, say, equal proportions of red light and green light, our visual system will not report that the color is red-green. Instead, our perception will tell us that we are seeing a yellow color. The color of yellow can also be created as a specific clean color. Every color we are presented for will be perceived as a single color, and we cannot perceive if the color is a mixture of two or more colors, or if it is a single color. Two spectrally different mixture of colors are called metamers, if the human vision sees the mixture as the same color. The details are lost. This deficit in our visual perception is utilized in a simple way to create displays that can produce millions of different colors. A display typically has three primaries, red, green, and blue. By controlling the amount of light the three individual primaries per image pixels emits, the necessary colors can be shown and render the intended image for the viewer. Why is it that a different output of light can look the same to us, or why are the details lost? Our sensitivity to light comes from our eyes' cones and the spectral sensitivity of these. We have 3 types of cones in our eyes, and each of them is sensitive to a range of wavelengths, long, medium, and short, with some wavelength overlap. As a side note, the 3 types of cones are all located in the central field of view, while there's only 1 type of rods, and the rods are located outside the central field of view. The graph in the lower right shows the normalized spectral sensitivity of each of our eyes' cone. When a spectral stimuli is received on the cone, the signal out from each individual cone is proportional to the sum product of the spectral stimuli and the individual cone's spectral sensitivity. This principle is utilized in any colorimetric measurement system. More on that later. The information of a registered color stimuli is now reduced to a set of 3 values, the magnitudes of L, M, and S. So our perception does not receive spectral data and hence cannot provide information of spectral details. In the graph, the standard 2-degree cone response of the human eye have been overlaid on the samples of the SPDs we introduced previously. The 2-degree cone response was chosen to limit the response to only cone response, as the cones are located in the central 2-degree field of view, also called the fovea. By inspecting the graph, it is seen that any spectral stimuli will always give a signal in at least 2 of the cone types L, M, and S, and that the signal is proportional to the sum product. It is also possible to see that the same set of signals from the triplet L, M, and S can be obtained by several different SPDs, causing metamers. The knowledge of the spectral sensitivity of the 3 types of cone is the basis to establish a metrology for the perceived brightness and colors by the human vision system. Photometry is the science of quantifying and describe the human brightness perception. Colorimetry is the science of quantifying and describe the human color perception. The science of the human perception of light stimuli began by studying and documenting human spectral sensitivity to light. James Clerk Maxwell first demonstrated that 3 primary colors, red, green, and blue, could be used to create almost any other desired color. He experimented using a group of observers who were asked to adjust the brightness of primary colored lights to match the color of a white target. In the late 20s, W. David Wright and John Guild continued similar experiments to evaluate how much red, green, and blue light was necessary to create any color in the visible spectrum. Their work taught us that there is a link between wavelength and the colors of the human eye can see. More importantly for us, the amount of each primary color necessary to produce each seen color could be measured across a set of standard observers. Wright and Guild also showed how colors outside the gamut could be realized by adding an amount of a color of the reference, which, in the end, led to the creation of CIE's 2-degree standard colorimetric observer. Wright and Guild's experiment provided a set of trichromatic functions, the X-bar, Y-bar, and C-bar. These color matching functions were standardized by CIE in 1931 and provided a standard representation of any color stimuli, given as the 3 tristimulus values X, Y, and Z. X, Y, and Z tristimulus values are calculated as the sum product of the spectral color stimuli and one of the color matching functions, and multiplied by a constant depending on what property is being calculated. For neutral color stimuli, in example, Illuminance, tristimulus values are equal, meaning X equal Y equal Z. The Y-bar color matching function is proportional to the standardized spectral sensitivity of the human eye given by the V-lambda curve. The color matching functions are used to calculate the tristimulus values of an SPD. The formula indicated in the two graphs are a little confusing. The tristimulus values are proportional to the sum product of the relevant color matching function and the SPD of the stimuli. With the tristimulus values, chromatic coordinates of various color spaces can be calculated. The CIE chromaticity diagrams are 2D representations of the possible color gamut. The earliest system, the CIE 1931, is shown to the left. A mixture of two colors will be located on a straight line between the two individual colors. The system is also basis for the concept of dominant wavelength and color purity. The main drawback is that the Euclidean distance between two colors in this system is not well correlated with the perceived magnitude of the color differences. The next system, CIE 1960, was a first attempt to get a better correlation between the Euclidean distance and perceived magnitude of color difference. This system was the basis for deriving the correlated color temperature. The next system, CIE 1976, was an improvement over the 1960 system regarding the perceived color difference. The system is the preferred system within the display industry, a metric for chromaticity differences for equal luminance stimuli. Let's describe some aspect of the CIE chromaticity diagram. We'll use the CIE 1931 as an example. The curved edge of the color gamut is called the spectrum locus and corresponds to the color coordinates for all monochromatic sources. See the wavelength in the diagram. There are no monochromatic sources along the straight line between the deep blue and deep red. Along the spectrum locus, the color purity is given the value of 1.0, and at white, the purity is 0. Colors with stimuli over a larger range of wavelength will tend to be located away from the spectrum locus. A stimuli with equal power at all wavelengths is called Illuminant E, E for equilibrium, and is located in the center of the diagram at 0.333. The curved line towards the middle of is the Planckian locus, also called the blackbody curve. Each point on the curve represents the thermal radiation from a perfect black body. The lines crossing the Planck locus represent colors that have a certain correlated color temperature. In a CIE 1960 diagram, these lines are perpendicular to the Planckian locus. Colors on the very right of the Planckian locus is what is seen at the blacksmith, while colors on the very left corresponds to maybe a supernova explosion. An example of a display color gamut is shown with the primaries RGB. The display can show all chromaticity within the triangle RGB, but due to limitation in the primaries output, the amount of possible chromaticities is reduced with higher and higher luminance. A lot of development is going on in making more pure and powerful primaries. Here are a couple of examples to illustrate how we calculate chromaticity coordinates and map them to the chromaticity diagram. To calculate the coordinates, we need the color matching function and we need the SPD of the light source in question. The first example here is a blue LED. Here we have drawn an example of the blue LED's SPD bounded by the dotted line seen in the plot to the left. The area on the color matching function corresponds to the tristimulus values x, y, and z. Tristimulus x is the area shaded below the red curve. Tristimulus y is the small area below the green curve, and tristimulus z is this large area below the blue curve. In the formula at the bottom, we're using up and down arrows to indicate large and small values. First, we see that our tri-stimulus X values is relatively small. Our tri-stimulus Y value is really small. And we get a very big value for tri-stimulus C. Our chromatic coordinate X is going to be small because for wavelength of blue, we are dominated by the large tri-stimulus C value on the denominator. Next, we calculate the lowercase y value. We have the same large denominator due to tri-stimulus C, but the difference here is that our tri-stimulus y component is even smaller. We have much less area underneath the green curve bounded by SDBD of the blue LED. Doing our same math, we get our y coordinate, which is even smaller than our already small x coordinate. We can now plot our blue LED in the chromaticity diagram in the lower left corner. Here we make the calculation for a red LED. In this case, our tri-stimulus X value is pretty big. Our tri-stimulus Y value is a little smaller, and our tri-stimulus C value is really, really small. There's almost no C component at all adding to the denominator of our formula, so our X coordinate is large. We have the same denominator for our Y coordinate, but we have a little bit less contribution from the tri-stimulus Y value, so our lowercase y coordinate is medium. In this case, for red, we plot our XY coordinates as shown in the diagram to the right and up in the middle area. Here is an example using the SPD of sunlight, a broad area defined by the dotted line. In this example, all our tri-stimulus values are about the same, so our chromatic X and Y coordinates in our formula are almost even. That puts us right in the middle of our CIE diagram. This describes the color of sunlight as white. Tolerance setting can be done based on custom parameters or on human perception of just noticeable differences. Maeda ellipses are a way to describe the just noticeable difference between colors in the chromaticity diagram, meaning how far away can you go on the diagram before the standard human observer perceives a noticeable change in color. We can use the Maeda ellipses to illustrate the improvement the CIE 1976 system gave with respect to a more uniform measure of color differences. Now we have reviewed how to quantify light and color values, the cornerstone in display metrology. These values and principles will continue to appear throughout this presentation as we look at display analysis methods and applications.
In this section, I'd like to take some time to make introduction of display measurement. Display technology has been rapidly changing over the past decade. Different display devices have different characteristics and optical configurations. When it comes to operation and driving techniques, we already have some different operation principles, such as LCD, OLED, and micro-LED, and so on. Even the same display type could have different applications. For instance, LCD has a variety of applications, such as smartphone, head-mount display, and TV, and so on. They all have different characteristics and configuration, so we might need different solutions for display measurement. As for light and color measurement, there are many characteristics to be evaluated. Most of modern displays are manufactured in Asia and shipped out to consumers and EMS over the world. There's a complicated supply chain to assemble a display device from so many components. To ensure the display quality, we need to evaluate displays, components, and product at each step of manufacturing process. This table shows a typical example of display characteristics to be evaluated in such process. For example, when you use imaging system, you can evaluate uniformity, mirror, pixel defects, and distortion, and so on. Those characteristics must be objectively evaluated with proper light measuring devices. When it comes to display measurement, luminance and color are most basic parameters. Normally, we use color matching function to compute color and luminance. Here we plot one example of display emission and color matching function. With those two spectra, we can compute tristimulus value XYZ. Chromaticity and luminance level can be computed from those XYZ values. As you can see from this equation, XYZ can be computed as wavelength integrals over spectral density weighted by color matching function. Color gamut represents a color range that can be reproduced. For gamut calculation, CIE 1931 XY and CIE 1976 U-V- are most commonly used chromaticity diagram. Both of them can be calculated from XYZ values. We often see many manufacturers emphasize the color gamut area of their products in their flyers of smartphone. But they sometimes never mention about which color diagram it is. This may cause some ambiguity. They should mention which one of them are used for gamut area calculation. Also, whether it is an area ratio or area coverage ratio, this also should be clarified. Area size ratio can be larger than coverage ratio, and it could be more than 100%. There's another way to define color rendering capability. That is color volume. Color volume is based on the fact that color rendering capability is depending on luminance level. Two-dimensional chromaticity gamut is not capable of representing luminance dependency, so it can be a misleading metric. This table shows an example color volume percentage versus gamut area percentage of an identical display. This table shows that we can see significantly different number between 3D color volume and 2D color gamut. If you want to measure color volume, there are hundreds of measurement steps to be required. It is recommended hundreds of points should be measured by changing luminance and color of displays to cover the entire 3D volume. Normally, high luminance has more capability to express more depth of color. This method will be included in an international standard, so if you are interested in color volume measurement, you can refer to the standard. Gamma represents relationship between input video signal and output luminance level. Display manufacturers need to fine-tune it in the production line in order to realize desired brightness and colors. Modern smartphones have different color mode which has different gamma curve, but generally speaking, default gamma is 2.2 for most of display devices. When it comes to OLED, gamma tuning process could be time-consuming process due to low luminance and multiple band and tap points required to be tuned. They need to tune individual voltage for RGB and adjust luminance and color to be within the tolerance so that different displays can emit same luminance and color. Uniformity is also one of the most important characteristics. These pictures represent typical non-uniform screen at different gray levels. There's also other word, Mura. Mura is more of a localized deviation, while uniformity represents imperfection across the entire screen. Uniformity and Mura are most often measured characteristics with an image-based light measuring device. Like uniformity, random defects can appear across the display. That can be introduced in manufacturing assembly processes or stress caused to the display. Mura is Japanese for blemish. Mura defects are non-uniform areas or bright or dark blobs across the display. We can see an example in the image to the right. On the top is a measurement image of a display with Mura. And just below, this is an analysis of the Mura using false color to show luminance differences. Other random defects may vary, but some notable ones that may be inherent in the display are lines and dots. Lines are sharp extended blemishes that only exist in the vertical and horizontal directions. Dots are stuck on dead or dim pixels. Dots can also be introduced into display layers, for instance, contaminant particles such as dust. Evaluating displays for random defects like Mura and dots or lines requires luminance and chromaticity analysis across the entire screen. This analysis is typically performed by image-based measurement systems, which can capture all visible areas of the display at once. Display emission is anisotropic. When you see it perpendicular to the screen, or you see from an angle, they look different. Directional view can be measured with light measurement device combined with goniometer to measure from different angles. Also, conoscopic solution can be used to capture the characteristic in one shot. Reflection of environmental light in the display screen reduce contrast and saturation, which are annoying and lead to visual fatigue. The geometrical details of illumination and reflections are complex. Measurements are typically done with several light sources and a goniometric system. For example, you may want to simulate sun or artificial light or ambient light. This picture represents typical result of reflection of display. You can see the highest peak, which is corresponding to specular. Also, haze and diffuse characteristics can be visualized. Time domain analysis is often measured by light measuring device. For short time modulation, some luminance meters or calorimeters support high sampling rate of data collection, so that users can capture luminance waveform. For flicker measurement, luminance meter needs to be used rather than oscilloscope because it is weighted to human visual perception and shows linear response to luminance level. Also, response time is often measured to see how fast display can respond when rapidly changing gray level. As I mentioned in the previous slide, display is time-modulated device. When we use light measuring device, we need to consider how to synchronize display waveform and integration time. Right top picture in this slide represents result of mismatch between display waveform and integration time. In this picture, blue line represents display waveform and red dot line is corresponding to each integration time. So in this case, we take a measurement twice. But as you can see from this picture, first sampling captures two peaks, while second sampling only captures a single peak. This means that regardless of the same sampling duration, measurement results could be inconsistent. This issue is induced by mismatch of display's driving frequency with integration time. So what we need to do is integration time should be integer multiple of display's driving frequency so that we can retrieve consistent and stable results over time. Here we want to discuss the difference between spot meter and imaging meter. Literally, spot meters measure a specific small area, while imaging systems normally capture entire screen. The benefit to using spot meters is high speed, less expensive, and accurate, so it's often used in production line to reduce the takt time. Imaging system is capable of measuring whole screen at once, but it can be influenced by viewing direction changes to display edge. There's actually many applications of imaging meter. The most typical use cases are uniformity and Muller measurement. Spot meter falls under two categories: filter-based spot meter and spectral radiometer. Filter-based spot meter uses color filters to create color matching function. It is high speed and high sensitivity, but accuracy depends on how closely color filters match color matching function. Spot spectral radiometer measures wavelength domain signal, so you can retrieve spectral data. Generally speaking, it is known as quite accurate for color measurement, but slow and expensive as compared to filter-based spot calorimeter. So if you need spectral data, you are going to want to use spectral radiometer. And if you only need chromaticity and luminance and some basic parameters, then filter-based spot calorimeter will be recommended.
Hi, we come now to the next section. It is about metrology and units of measurement. You will learn about the quantities typically used to characterize a display, and we will talk about traceability and the photometry. Let's start with some basic thoughts about metrology. You see here the metrology as defined by the International Bureau of Weights and Measures. It reads: the science of measurement embracing both experimental and theoretical determination at any level of uncertainty in any field of science and technology. Well, that sounds quite theoretical. So what does it practically mean? I think we can all agree that for successful communication we need a set of terms with a common meaning. That is essentially all what it is about. Scientist community agree on a common vocabulary, best practice, units, and so on. That happens in standardization bodies and in national metrological institutes like the NIST or the PTB or the CRIS and so on. More concrete on measurements, we want to determine a value, and therefore we need a unit which defines a scale and an understanding what this measure means. There are many different bodies for standardization in the field of display measurements. I want to point out a few of the most important ones for you. There is the IEC, the International Electrotechnical Commission. It is engineering and technical focused. There is the ISO, the International Organization for Standardization. It is the highest body if it comes to standards. We have the CIE, the International Commission of Illumination. They define the basis of light measurements. And we have the ICDM and the National Committee for Display Metrology. They have the most practical compilation of recommendations of real-world applications. Let me give you some more details about the 4 organizations. Let's start with the CIE. It gives you the fundamentals of photometry and colorimetry. A very important standard is the Terminology Guide, the ELV, which defines a vocabulary to be used in context with light measurements. The IEC is very important if it comes to data sheets, for example for displays, but also for measurement devices. There is a more fundamental technical committee running the TC 110. It has the target to define a standard of terms and definitions, letter symbols, essential ratings and characteristics, measuring methods, specifications and quality assurance, and related test methods and reliability. I have listed a few more important publications from the IEC. The ISO has the most fundamental standards, for example, on ergonomy of the use of displays, but they have, for example, also the standard for calibration and test laboratories, the ISO 17025. The ICDM has the most valuable pool of practical experience. So if you want to get help for your unsolved problem, so please visit their database of information. They have more than 500 pages of distinguished expert knowledge. Let me come to measurement units. The basic unit of photometry is the Candela. I have copied the definition here in written form, but I want to focus more on its meaning. Light is of such importance that it got its own basic unit. So it's 1 out of 8 fundamental SI units. As most SI units, they are historically described by the physical experiment. Here it used to be a candle, which gave the name of Candela. Today they are replaced by better defined experiments. The Candela is today linked to the radiometry. Hence, it is linked to the definition of power in watts by a fixed constant, the so-called KCD number. Practically means you take a laser in the green, very close to the peak value of the V lambda curve at 555 nanometers, and if it has 1 watt, it has an efficacy of 683 lumen per watt. That's defining the scale of the photometry. The other colors are then linked by the photopic luminous efficiency curve, also called the V lambda curve. There are 4 measures and units in both radiometry and photometry. Radiometry is the science of measurement of radiant energy, including light, in terms of absolute power. Photometry is the science of measurement of light in terms of perceived brightness. It includes the physiological sensitivity of the human eye. As we have seen before, for the Candela, the corresponding quantities are linked by A, the KCD constant, and B by the V lambda curve. The 4 meaningful quantities are described here. So flux can be either radiant flux or luminous flux. It describes how, for example, a source is emitting power. Radiant intensity or luminous intensity describe how the flux propagates in a certain angular cone. Irradiance and illuminance describe how much arrives at a certain spot, so for example at your table or at a detector. And radiance corresponds to luminance. It describes how much is emitted from a surface, so this is the most important unit for display measurement. So let me give you a better feeling what the quantities are used for. I start with the candela or the luminous intensity. It is the amount of luminous flux from a point source emitted in a given direction and registered in the far field. So if you see here the point source, the light is propagating, and at a certain point you have an area dA, and there you register the amount of light arriving here, and the luminous intensity is then given what is propagating through this cone. What is it used for? For example, if you want to make goniometry, you go far away and measure the light coming to your detector, describing a point source, or in technical means, for example, a projector or headlights of a car are typically used with or characterized with luminous intensity. Now we come to luminous flux. Luminous flux is the amount of light radiated by a light source. It is the luminous intensity integrated over all directions. It may be best remembered when looking at a typical detector, the integrating sphere. So it experimentally does what is described above. It integrates over all directions. The typical use case is to measure efficiency, for example, for lighting products or for individual LEDs. Illuminance is the amount of luminous flux falling on a surface. It is independent of the type of surface, so it can also be a virtual surface, but actually the light is going through. The unit of illuminance is the lux. It is used, for example, for receivers or photometers, and especially also for safety. So if you talk about exposure, for example, of skins, you talk about illuminance or irradiance. Finally, we come to luminance. This is the most commonly used measure for displays. It describes the luminous emission of a surface. Luminance is used to specify the amount of luminous flux traveling in a specific direction. Hence, it includes both an area from which it is emitted and a certain cone in which it is propagating. So it results in a unit of candela per square meter. Here is shown a typical probe to measure luminance, and typical use cases are imaging photometry, of course, quality assurance, and especially displays. A few words to color spaces. You have learned about the CIE color spaces in the section before. They are most general. They are the right color spaces to measure, and it describes the full color space the healthy human eye can see. But for displays, also other color spaces are of highest importance. We can call them technical color spaces, or we can call it color gamut of a device. What is the difference? Displays are using additive colors. Hence, the color space needs to describe additive colors. You have three primaries, and all perceived colors are mixed by superposition of the three primaries. On the chart, you can see the CIE full color space, and there are the outlines of three commonly used technical color spaces. The smallest of which is the Srgb. It might be a bit old-fashioned these days, however, it is probably still the most popular one for practical means. Every device can display it. Most phones these days are able to show a much larger color gamut, for example the DCI-P3, that is the middle one. It gives much more vivid colors and more natural experience. I outlined also the recommendation 2020. It gives a kind of a maximum color space. It is intended to be future-proof in a sense that it seems difficult to realize even a large color space. It uses essentially monochrome light at the red, green, and blue. The technical recommendation contains more than just the color gamut. Here is an example for Rec 709 for high-fidelity imaging. The recommended color space is equal to the Srgb definition, but it also defines the number of intensity steps, 256, and how the steps should be linked to the intensity. That is a nonlinear scale because the human perception is non-linear. The just noticeable difference is much smaller on a bright display than it is on a dark one. Hence, we need more steps in the dark gray states. It can also come along with the requirements for matrix resolution and frame rates. Recommendation 2020 results in even higher fidelity imaging. So the familiar 4K and 8K definitions are mentioned here. High frame rates are defined. This is used especially for fast-moving content like in gaming. For color gamut, it defines essentially monochromatic light sources at 3 well-chosen wavelengths. The intensity raster needs at least 10 by the 12 bit. And it also increases the dynamic range of the display because this becomes feasible with OLED and micro LED displays.
Now we understand the basic building blocks for measurement. Let's discuss how these principles are applied by equipment. In this next section, we will introduce the measurement tools or meters used for display metrology, the impact of various system specifications, and the importance of using calibrations to ensure measurement accuracy. I'm going to start by introducing a metrology system called a spot meter. Spot meter is a device for spot measurement, so which measures a small spot area. Some instruments have viewfinder like digital camera so that you can check the exact area to be measured. This kind of device is widely used not only in laboratory but also in production line. In terms of field of view, imaging meter is capable of measuring a much wider area than spot meter. However, in some applications, we still want to use spot meter for color measurement. First of all, accuracy has to be considered. When it comes to filter-based instrument, accuracy of spot meters is normally better than imaging meters. Imaging meter could have some difficulties with having perfect color filters that match color matching function. Second, cost. If you have limited budget or plan to purchase multiple devices, then spot meter could be normally less expensive and recommended. Also, if you want to hold a device in your hand, then portability could be also important. And next is data handling. Image data is huge and it's sometimes too much. With spot meter, you can compress the information to limited data size. That compressed data might be sufficient for some applications. Viewing direction dependency. When you use imaging meter, you need to measure the edge or corner of the UT from an angle. In other words, this is called a vantage point. If you prefer to measure your sample from a vantage point that is close to human visual system, then imaging device could be a good option. But if you want to avoid the effect of the vantage point, then spot meter will be necessary. Spot meter falls under two categories. This table shows 3 different types of spot meter for light and color measurement. First and second lines represent filter-based meter. The difference between the first line and the second line is whether or not they have a viewfinder. The second line is a filter-based meter with viewfinder so that you can clearly see the measurement area. This is often used for LED and instrument panel measurement because they could have a specific small ROI to be measured. Spectrometer could be highly accurate, but of course it's depending on the quality of the hardware. When it comes to spot measurement, we have a variety of application examples. For smartphone measurement, spot meter can be used for gamma tuning process, for example. For small micro OLED from AR/VR application, small spot meter can be used for color and luminance measurement. Also, backlight measurement. You might want to measure the contrast of the backlight with spot meter. This is just a part of example. In here, I want to dig into optical design of spot light measurement device. Filter-based spot calorimeter splits an incident light into 3 XYZ color components. So it normally has 3 or 4 color filters and sensors to individually measure tree stimulus XYZ values. Also, small acceptance angle could be preferable for certain type of displays that have larger viewing direction dependency. Spectral radiometers have a variety of optical configuration, and this picture is just one of the examples. Unlike the filter-based device, spectral radiometers have normally grating inside to retrieve wavelength domain signal. Now let's take a look at metrology systems that apply time-resolved analysis. As all you know, display is not static. But normally we are not aware that screen brightness even with static image is changing over time. This is because it is a high-frequency event, so you can't see it. This kind of brightness variation over time is what we call waveform here. You can measure and visualize waveform by using a sensor. Specifically, Luminance meter is the most authentic device that you can use for characterizing waveform. This picture represents just one example of OLED waveform captured by a spot meter. People actually don't see it through their eyes, but which can be visualized through a sensor like this. Waveform, specifically flicker, should be measured by a proper luminance meter because it is weighted to human visual perception. There are some critical specifications to be required for waveform measurement. First of all, sampling rate. There are several recommendations in international standards. In order to capture high-frequency signal, sampling rate should be high enough. But there's a trade-off between sampling rate and light sensitivity, so we need to optimize the balance between those two. For flicker measurement, a few thousands hertz of sampling rate should be enough for most of use cases. When it comes to light sensitivity, high light sensitivity is required for such short exposure sampling. Linearity is also important because display waveform could have wide amplitude from low luminance to high luminance at the same time. Luminance meter should have enough dynamic range to capture it. Calibration is related to human visual system, and well-calibrated luminance meter is recommended because they have correlation with human visual system. Gray or RGB cameras with commercially available CCD or CMOS sensors are not appropriate for this kind of use case. When you analyze waveform, there are two ways to do that. First, time domain analysis. This is very simple. You are going to use the raw waveform data as it is. Some luminance meters have hardware low-pass filter inside to cut off high-frequency noise, such as outlier. so which might be needed for this kind of analysis. Second, frequency domain analysis. You can get frequency domain signal by applying Fourier transform to the raw signal. After you get frequency domain signal, you can easily apply frequency domain filter. The low-pass filter is one of the such filters that can be applied in frequency domain signal. The signal waveform includes outliers, so you might want to get rid of it. For such purposes, you can use low-pass filter. When you want to analyze waveform in frequency domain, high-frequency component could appear as aliasing. This aliasing noise is an unwanted artifact induced by undersampling. Digital low-pass filter cannot remove such aliasing, but hardware filter can do that. Let's take an example of actual display waveform. This is a typical LCD waveform. LCD is inverting positive and negative frame alternatively in different frame. In such case, Vcom reference voltage should be well balanced from positive and negative voltage. Otherwise, absolute voltage between the display electrode and Vcom is different in different frames. This causes luminance difference in different frame, which results in flicker artifact. LCD often inverts the polarity at side-by-side pixels in order to reduce the flicker artifact. So if you display a specific pattern on screen, flicker would be more likely to be visible to human eyes. OLED has totally different waveform characteristic from LCD. Specifically, smartphone OLED has PWM to dim the brightness. PWM is usually high-frequency component and is observed as sharp transition in waveform shape. On the other hand, there should be a gradual luminance reduction or increase in each frame. This luminance reduction or increase is caused by leak of current on the TFT. VRR means variable refresh rate. In other words, we might call it dynamic refresh rate. This has been one of the major technologies for gaming industry. With this technology, display's refresh rate dynamically varies over time in order to avoid screen tearing and stuttering induced by frame rate inconsistency across display and GPU. In this case, waveform could be non-periodic waveform, unlike conventional static refresh rate. The analysis of non-periodic waveform is challenging because it will be composite of multiple frequency components and the spectrum varies over time. Conventional flicker metric might not be sufficient, so we might need to use new algorithm to quantify such characteristic.
A very necessary and valued piece of measurement equipment is the image-based measurement system. An image-based measurement system is based on an image sensor chip. In principle, this system is an array of small spot meters that all can operate simultaneously and measure the device under test with a very high spatial resolution. Some of the advantage in image-based system is contextual evaluation, uniformity, gradient, contrast, mirror, distortion, location identification, and severity of defects like pixel, lines, blobs, simultaneous measurement of multiple regions of interest, LED arrays, pixels, subpixels, determining dimensions, distortion, and focus quality projection displays, and performing advanced analysis with multiple analyses possible per captured image. Imaging systems have a few fundamental components. The image sensor is where the light is received by the system and converted to digital signal. Image sensors vary in performance based on a number of factors we'll describe later. Imaging systems used in display metrology are typically called imaging photometers or colorimeters. These systems have optical filters and calibration that match the standard human spectral response defined by our CIE color matching functions we introduced earlier. This ensures accurate luminance or chromaticity measurement. For these kind of measurement, a photopic or colorimetric filter system is needed to capture light as weighted by the standard CIE functions. Light enters the system through the system optics, a lens which directs light to the system image sensor. Depending on the lens applied, light can be captured and directed in different ways. Image sensors are rectangular arrays of photosensitive elements or photodetectors called sensor pixels. Photons captured in each sensor pixel are converted to digital information to form a two-dimensional image. The two main sensor types are CCD and CMOS. There are differences between the sensor types, but both have been proven for display metrology in recent years. Here are shown some illustration of a sensor pixel array and the makeup of a single sensor pixel, where photons are converted to electrons. Each sensor pixel has a particular capacity, called its well capacity or well depth, which determines how many electrons it can capture. The number of electrons in each pixel determines the quality, the noise of the measurement. The accuracy is determined by calibration and by the quality of the sensor and electronics, resulting in the repeatability of the system. An image sensor's characteristics impact both the amount of data and the accuracy of the data captured by the imaging system. Some of the most critical characteristics are resolution, size, noise, and dynamic range. First, resolution impacts the number of discrete data points captured by the imaging system. This is limited by the number of pixels on the sensor. High imaging resolution enables us to identify and measure more details while capturing the entire field of view of the device at once. When a 1 megapixel sensor are used to measure an entire backlit keyboard, we can see there is less details captured than when a 29 megapixel is used. Higher resolution enables an imaging system to perform measurement on extremely small devices, features as well such as pixel level defects or pixel and subpixel level measurement and detection, which is used for display qualification and processes like pixel uniformity correction. The size of an imaging system sensor limits the field of view that can be captured in a measurement image. Another impact of sensor size is the size of the individual sensor pixels. As resolution of the sensor increases, pixel size is reduced to fit the sensor dimension. This can potentially impact pixel well capacity or light captured at each sensor pixel. There are important trade-offs and considerations to keep in mind when choosing an imaging system with a particular resolution, field of view, and accuracy. The sensor size may limit certain factors while improving others. All measurement systems capture a certain amount of inevitable noise. Noise limits the precision and repeatability of measurements by introducing random variation in images. The primary source of noise in any measurement are read noise, shot noise, thermal noise, and pattern noise. There is a lot of information in the given table, but luckily this is a virtual presentation and you can pause and study the table. An imaging system's signal-to-noise ratio, or SNR, is a measure of the expected amount of noise captured by the sensor compared to the true signal of a source. Ideally, the imaging system would capture an image of the display with perfect precision, each sensor pixel receiving and converting the same number of photons to electrons as are output by the device, without introducing other electrons. But as we have seen, due to the inherent nature of noise, this is impossible. The combination of optics, sensor performance, thermal cooling, electronics, image processing, calibration, and other aspects of the imaging system must control noise well enough so noise only has a minimal impact on the result. Signal-to-noise ratio is critical when looking at subtle differences in photometric measurements. For example, detecting small low-contrast defects or variation in a display. In these cases, there's very little signal received by the imaging system, so the impact of noise could have a great effect. Here we are showing an example of signal-to-noise ratio. The two plots shown here are from real measurements. The task was to detect a subtle difference on a bright background. The luminance variation is given in units of standard deviation of the bright background. Using the standard deviation as the luminance unit emphasizes the noise issue and makes it functional for any luminance level. The spot with the subtle difference to the left was positively detected in approximately 40% of repeated measurements, meaning 60% false negatives. A signal of magnitude, approximately 3 standard deviation, will often just blend into the surrounding background level and become undetectable. The spot to the right was measured by averaging 4 individual measurements. This enhanced the spot luminance and lowered the background noise, both in units of sigma. The detection rate we are now at is nearly 100%. The change in signal to noise is a factor of 2. The lesson to be learned is that we need enough electrons to beat the noise. The next imaging system component we'll discuss is the filter. Imaging systems employ different methods of filtering light for photometric and colorimetric measurements, which aim to provide accurate luminance and chromaticity values in the measurement image. One method employs a rotating color filter wheel, seen on the left. Here, the system works by capturing tristimulus values in 3 or more channels with color filters that, combined with the sensor and optic spectral sensitivity, closely matches the CIE color matching functions. Light enters the imaging system through the system's optics, and sequential exposures are made through each of the color filters as the wheel rotates. A full color image is a combination of 3 or more full sensor resolution exposures. Another method is a Bayer pattern color filter, or Bayer mosaic, shown on the right. In this case, the color channels are realized directly on the sensor array with alternating rows of red-green and green-blue pixels. Light enters through the system's optics, and each sensor pixel receives the signal for a single color channel. A full color image is produced in 2 ways. In the first, a process called demosaic average the input of nearby sensor pixel to obtain an approximation of full color for each pixel, which lowers the effective resolution of the image, meaning the output image resolution is lower than the sensor resolution. As an alternative method, pixel shift can be used. In this case, several images are captured. The sensor is moved or shifted to a new position for each image, providing each pixel on the sensor with more accurate and complete color values, and maintaining resolution of the image or matching the true sensor resolution. For both systems, they need the same number of measurements to achieve the same spatial resolution. Both filter wheel and Bayer pattern system must be calibrated to align their response to these color matching functions. This is done by supplying the image system with calibration data either as a spectrum from a spectrometer or by measuring golden samples. Calibrations will be introduced in more detail later in this presentation, but it is worth mentioning that image-based color measurement uses colorimetry and relies on calibration to ensure accurate system response according to the standard CIE color matching function. The reason is that it is impossible to make a perfect match to the CIE color matching functions. One might get close for a complete static system, but any change of the lens, an aperture shift, etc. will for certain change the spectral transmission, and this will deteriorate the performance without a compensating calibration. On the left here, we show the innate spectral response of each color filter method in the dotted lines compared to the standard color matching functions in solid lines. The matrices on the right shows how the corrections are dependent on the system's spectral fit to the color matching functions. A bold letter indicates a high magnitude matrix component, and the epsilon indicates a small correction. For a perfect match, the epsilon will take the value of 0. The last component in a measurement system is the optics. There is a variety of lenses that can be paired with imaging systems to direct light from the display to the imaging system sensor in different ways. The point in metrology is to use an optical component that captures all the information about the display that is important for the evaluation. In general, optics are chosen for the imaging systems on the basis of what is the field of view, what is the focus we need to obtain, what kind of apertures do we need, do we have enough image quality, and do we have enough repeatability and accuracy if the focus or aperture is changed. Typical types of lenses are wide field of view lenses for large screens, TVs, narrow field of view lenses for mobile displays, and even narrow view, we would use microscope lenses. Typically, that would be for R&D. Some measurement tasks need optics that are specifically designed for a special task. Here we can mention eye-near measurements on AR/VR headsets, where the entrance aperture must be at the very front. Another example is measuring the angular performance of a small source or a display in one single measurement. Optics are developed that measures the entire angular field of emission and maps it into a 2D measurement, where each sensor pixel location corresponds to a certain emission angle.
As the last measurement instrument, we will discuss a spectral radiometer. Well, a spectral radiometer is essentially a spectrometer with a defined, engineered and calibrated intensity scale that allows to measure radiation on an absolute scale. The physical principle of a spectrometer is to split up the radiation into spectral components. The means to do this are either a prism or a grating, both having their advantages and disadvantages. Refraction at a prism has the advantage of a very high throughput. Refraction is dependent on the refractive index. This tends to be much more temperature dependent than a grating. Of course, it can be optimized with corresponding glasses, but it is difficult to come into the stability range of a grating. A minor drawback is that the resolution depends on wavelengths, hence it is more difficult to establish a reliable wavelength scale. With a grating, we call the split up diffraction. Diffraction only depends on the geometry. The wavelength scale comes naturally linear in angle, and the temperature sensitivity can be engineered very close to 0. Minor advantage is that also the accessible spectral range is larger, especially in the UV range. One way to build up a spectrometer is to use a scanning approach. You see here the outline of a double monochromator. The light is launched on a slit, It is collimated to hit the grating, and a second mirror is used to image the separated wavelengths to an intermediate slit. The same thing is done again to remove stray light. Hence, we receive a very pure monochromatic light after the exit slit. The two gratings can be rotated simultaneously. Typically, several detectors are used to enhance the spectral range, and the range of the grating can be selected to optimize throughput in several wavelength ranges. This results in a huge spectral range, great dynamic range, and a high stray light suppression. It can be used as a reference instrument and as a most versatile device for scientific applications. More commonly used are array spectrometers. Their main advantage is speed and simplicity. That's because they have no moving parts. There are several designs of the monochromator. Sketched here is a cross-Czerny-Turner design. The advantage of this design is a very high purity of the color split up, and yet a quite compact footprint. Instead of the scanning grating, a linear sensor is used to record the spectral components of the radiation. The sensor can be either a CCD or it is made in CMOS technology. Measurement times of a few milliseconds are standard. With CMOS, even microseconds are feasible. This results in a very fast and robust device as needed for quality control in production, but it is also widely used in R&D applications. Now we come to the point, what is key when you want to select a spectroradiometer? Well, as I said, the difference between a simple spectrometer and a spectroradiometer is the intensity scale. A radiometer needs to take care about the y-axis of the spectrum. That starts with a suitable optical probe, the guidance of light into the spectrometer, a fixed or reproducible interface between probe and meter. For the spectroradiometer itself, the key performance parameters are straight light performance, bandpass, linearity, and stability and repeatability. That is, for example, in respect to temperature or transport. Last but not least, it is important to take care about the calibration errors. Crucial is, of course, the wavelength scale, but you need also a traceable calibration to the national metrological institutes. You want low measurement uncertainties, and a regular recalibration and audit are required to maintain performance and follow best practice. A few words to different sensor technologies. The high-end sensors are back-illuminated CCD arrays. They feature overall the highest sensitivity. This is especially pronounced in the UV and the blue wavelength range, as can be seen in the diagram. They feature a very high dynamic range. Hence, they are best in class, but they are also a little bit pricey. In recent years, CMOS technology is catching up. They are definitely the fastest, and they allow for their increased pixel numbers and hence higher resolution. There are also cheaper devices that can be equipped with standard CCDs. We define one key performance parameter as linearity. There are two aspects. The dark current compensation is usually the largest component in nonlinear behavior. It can largely be suppressed by cooling the sensor. In the top graph, you see some examples for dark current behavior for cooled, uncooled, and stabilized devices. First, you see that the dark current contributions are mainly an issue for long integration times, for example, for measuring a dark display. And second, you see that the effect can be nearly eliminated by cooling the sensor to minus 10 degrees C. For all sensors, a full-scale linearization is recommended. All technologies have certain amount of nonlinearity which can be corrected. Last but not least, I would like to mention dark current compensation. That can be done by having a shutter in the system. A dark current can be measured with a closed shutter even in production line in a regular period. The dynamic range of a system is a further concern. The dynamic range in a single measurement is defined by the sensor performance. In the graph, you see comparisons of cooled CCD, uncooled CCD, and CMOS technology. Again, the highest performance is achieved by a cooled CCD. In the system, you can also introduce an optical filter to further increase the dynamic range of the overall system. Stray light performance is mainly attributed to the monochromator. One way to compare stray light performance is by the use of a cutoff filter. In red, you see the spectrum of a tungsten lamp. Now you can use a cutoff filter at 450 nanometer, for example, which eliminates all light with shorter wavelengths. Signal in this wavelength range is caused by stray light. You can see that the best performance is achieved by a scanning double monochromator. It suppresses stray light up to about 7 or even 8 decades. An array spectrometer is naturally much higher in stray light. But you also see here that there is about 1 decade difference between two different windows, so there are big differences. The effect on your measurements is highly complex and depends on the source you want to measure. An example is given here. In this comparison, a high-end spectrograph is used. A digital compensation of stray light is applied, which reduces stray light by a reasonable factor. Colored LEDs can be affected up to about 1/1000 in color space, that is the XY color space. Of course, this can be more significant for a spectrograph with lower performance. In the last slide of this section, I would like to mention that spectroradiometers can be combined with imaging colorimeters. Why would you do that? Spectroradiometers are considered the most accurate measurement devices both for color and luminance. The accuracy is independent of spectral variation, and you can transfer the accuracy with low loss to the 2D image. That gives speed because you can measure simultaneously all color channels and the spectrum. And the measurement scope is high because you can do everything you would do with a normal imaging device.
Each piece of metrology equipment is characterized by a set of specifications. This section will list and explain some of the most important specifications and why they are important. Metrology equipment have a long list of specifications. Many of these are common among a variety of measurement devices, and some are specific for a certain equipment type. The value of a certain specification can depend on the way the individual manufacturer chose the circumstances and the method to derive certain values. Therefore, many of the good specifications have several footnotes for explaining and specifying. I cannot cover all specification in detail during this short course, so the next slides will cover some of the key specifications for different types of equipment. This should help users understand what the specification mean, why they are important, how to use the specification information to choose a metrology tool. Most importantly, enable the user to ask relevant questions to the specifications. Logistics specification, as shown on the list, except for the last one, are important to decide if the equipment is at all practical and possible for the space available, connectivity to necessary auxiliary equipment, and for the metrology task at hand. Any measurement result is a mixture of trueness and precision. Trueness is the closeness of the measurement result to the true accepted value. The accuracy of a test method is described by trueness and precision. While precision is the spread of the individual measurement, trueness is a bias. We can get measure of both trueness and precision. With unaltered conditions, we can repeat the measurements many times, whereby the average value is taken as a high signal-to-noise ratio quality value we compare to the true value. Hereby we reduce the impact of noise into our accuracy determination. The found deviation is called the trueness. The precision is determined by calculating the standard deviation of the repeated measurements. Normally, the precision is stated by using a coverage factor, K. K equal 1 corresponds to 1 standard deviation, and K equal 2 corresponds to 2 standard deviations. If a measurement's precision is given as 1.2% with a k-factor of 2, it means that a measurement result will be within the range plus minus 1.2% of the truth with a probability of 95.4%. Let's discuss general accuracy specification in a little more detail. The absolute accuracy is established by comparing measurement result to preferably a primary laboratory like NIST, NPL, PGB, EGL, etc. For companies following ISO 9000 or similar, a master measurement equipment must, at a regular interval, be shipped to an accredited laboratory for calibration. After comparison to a known value, the instrument will, if necessary and possible, have its trueness corrected. This can be done by uploading a new calibration file, entering a new value, the turnover screw, etc. The precision of the instrument stays the same. Upon return, the company can perform a comparison of their working instruments to their newly calibrated master instrument for transferring the calibration. For calibration of both types of colorimetric and spectroradiometric instruments, an incandescent lamp is used. The lamp is operated so its spectral emission is approximately as a blackbody radiator at a temperature of 2856 Kelvin, the Illuminant A. The reason for using an incandescent lamp is historic, and that the driving of an incandescent lamp can be done with a high level of stability and precision. A given accuracy is not a guarantee for the quality of all measurement results. The accuracy was established under recommended measurement condition. The trueness is maintained if the ambient conditions are appropriate, like temperature, airflow, ambient light, etc. In order to maintain a high precision, the sensor must be operating in close to optimum conditions, where the signal-to-noise ratio is sufficiently high. If the sensor is not loaded with sufficient photons to create enough electrons, the noise will deteriorate the measurement quality. This does not mean that low luminance measurements are less accurate. It means that the measurement takes longer time to get the needed accuracy. Even with the best equipment, there are many ways to make a bad measurement. Experienced laboratory personnel is very important in metrology. Not that they are any cleverer than younger personnel, they just have had the time to make all the mistakes by themselves and learn from it. The luminance and color measurement devices operate on one of two principles, either as a colorimeter, a filter-based, or as a spectral radiometer, spectral information. Both principles provide trisimulus values and hence luminance and color values. Both principles are realized as a spot meter type with one sampling area. The colorimeter principle is also realized as an imaging system, a large array of spot meters. The realization of an imaging spectral system has been done, and a few pieces of equipment exist. These are not, to my knowledge, very practical in display measurements. All equipment types should specify the minimum and maximum measurable luminance, the accuracy and repeatability of both luminance and color, dynamic range of the system, not just the sensor, and the field of view. Let's go through the specifications one by one. Minimum and maximum measurable luminance. The minimum luminance is important for low light application, as how dark can the display be, or test of light liquids. The maximum luminance is important for high light level application, as characterizing light sources by direct measurements, and maybe even characterize luminance variation over high luminance area. Accuracy and repeatability of luminance and color. Previously, we discussed the accuracy specification of measurement equipment. The repeatability is always important for the quality of the measurement, but a series of measurement with a certain variation can be a result of the instrument performance. But what if it is the device under test that might have a stability problem? There's a lot of time dynamics variation in a display correlated to the refresh rate of the display. Time variation can be caused by badly chosen exposure time in an unsynchronized system, or it could be real fluctuation caused by the display driving scheme. System dynamic range. The dynamic range is specified as the ratio between the maximum number of electrons possible and the read noise, typically given as a value in the decibel scale. It's a measure of the number of signal levels that can be resolved. This is a very important specification for both the imaging system and for the spectroradiometer. In any measurement with the two devices, there will be some variation in the signal level in the sensor pixels collecting either the spectral or the image information. The aperture and exposure times will be set to maximize but not overflow the signal in any pixel. The quality of the signal in pixels with less signal is dependent on the dynamic range. Field of view. If too small spatial information is missing, and if too large, the sensor is only utilized partly. Both the spectroradiometer and the imaging colorimeter can utilize the presence of the many pixels in various ways. With the 3-parameter resolution, saturation level, and averaging, a lot of flexibility is present. Averaging of images is a simple way of increasing the signal-to-noise ratio for all pixels by collecting more electrons. The cost is takt time. Maximizing saturation have the same type of effect as averaging images, but is much more limited as we don't want overflow in any pixel. The cost is also takt time. Resolution. If there's more than sufficient resolution, the image can be binned to create pixel that holds more electrons. Here the cost is resolution. The spectroradiometer have a few extra specifications concerning the wavelength properties. The wavelength range, the wavelength resolution, the spectral bandwidth, the wavelength precision. The range of wavelength is a choice the user makes at purchase. There do exist systems where the range can be changed utilizing a carousel with gratings. The wavelength resolution is the ratio between the wavelength range and the number of available pixels. The spectral bandwidth is a measure of the wavelength resolving power. The wavelength precision is how precise is the wavelength scale realized in the pixel array.
A final and critical important point to make about metrology equipment is the need of calibration. Let's get started again with the definition. I'm using here the definition of International Vocabulary of Metrology. So it reads, definition of calibration. Operation that, under certain conditions, in a first step establishes a relation between the quantity value with measurement uncertainties provided by measurement standards and corresponding indications with associated measurement uncertainties, and in a second step uses this information to establish a relation for obtaining a measurement result from an indication. Wow, that is heavy stuff. Let's get into it. So let's get a little bit closer to practical meaning. It is comparing the reading of a measurement instrument with an accurate standard to determine any deviation and correct for errors. So for us, we call a standard when we have a luminance source with a very well-known luminance. For example, if we have values from the NIST. We measure with our device and tweak until the reading is the same. That is the first part of it. But the tricky part is the measurement uncertainty. It can become rather complex to understand how errors accumulate from the NIST values to our final measurement. A warning from Wim is calibration should not be confused with adjustment of measurement systems, often mistakenly called self-calibration. Often you will hear traceability along with calibration terms. How can measurement be traceable? Metrological traceable is a property of the measurement result whereby the result can be related to a reference through a documented, unbroken chain of calibrations, each contributing to a measurement uncertainty. So in the picture is depicted, the National Meteorological Institute implements the basic physical definition of the Candela. With that, they create their own standard with the lowest possible uncertainty. From there, the industry can purchase calibrations or calibrated artifacts from the NMI. You will get it with values and with uncertainties. And that is now your reference standard in your lab. And you can use it to do further calibrations. Be aware that every step will enlarge the measurement uncertainty. And the radio and photometry usually uses lamps and not detectors to maintain the unit. Some expressions are often confused. For me, this schematic was very useful to understand and memorize. If we talk about precision, it is about the spread of measurements. It is typically, under good conditions, a property of the measurement device. That's simple to remember. Bad devices will scatter, good devices read always the same. But it does not mean that it is correct. Correctness is another dimension. It indicates, in an average, how well the measurement hits the correct value. Even here note, what is correct? That is, for example, if you get your values from NIST, you value plus minus the uncertainty. So it's not a one value, but it's a whole range. And now, an accurate measurement we call something which fulfills both. It is precise and correct. As an example, let's go through the calibration steps for a spectroradiometer for luminance. In the first step, the wavelength scale needs to be established. This ensures that each pixel of the detector reads the correct wavelength. Typically, for this procedure, line lamps are used. For example, mercury, xenon, or argon, or also some laser lines are suitable for such a procedure. The advantage is that the atomic lines don't need to be recalibrated, they are physical standards. In a second step, a spectral calibration is applied. For that, we use traceable standards, for example for radiance. The spectral calibration is crucial for the color accuracy. On the right side, in the top graph, you can see the implementation of such a luminance standard. A sphere is used to make a homogeneously emitting area. It features a well-defined aperture in which the values are valid. Typically, it uses a tungsten lamp as a light source, which can be controlled by the current control, or it features a monitoring detector in a closed loop. Usually, a color temperature close to the well-defined CIE illuminant A is used. That is at 2856 Kelvin. In the graph below, you can see the process. Green are the tabulated values from NIST or PTB or others. Red is the raw reading of a spectral radiometer. That results in a correction factor for each pixel, which is displayed in blue. So applying this correction factor to each pixel results in the green line at the end, and thereby the spectrometer is calibrated. Sometimes it is beneficial to add a third step. That is the calibration for an absolute value. By using of an integral reading for the spectroradiometer, systematic errors can be reduced and hence the accuracy can be improved. Metrology of light is an art. With electrical or mechanical measurements, you usually get very low uncertainties and the scale is easily maintained. With light and radiation, this is different. That is because both light source and detectors are not as stable as one would wish. In the end, it is a lamp which can age, break, or other things can happen. Hence, with light, it is a very good idea to have something at hand to verify your scale. That is what this slide is about. If you need a standard to quickly verify your scale, for example in a factory, such luminance standards might prove very practical. With a tungsten lamp, you have a long stabilization time and cannot carry it easily around. This standard is based on the LED. It is temperature stabilized and ready in a short time. So you have stable color coordinates and luminance value, so you can simply read if you get the right values out of your spectroradiometer. You have a stable spectrum, you can monitor if the spectral shape is changing, and you have even a blue peak, which allows you to monitor the wavelength scale. And the device is largely independent of ambient conditions. Maintaining systems aligned, for example in a factory, is of highest importance. There are essentially two philosophies how this can be done. On the left side, we have the golden sample method. You use a reference station in your factory which defines the base truth. Typically, these reference stations are equipped with spectral radiometers. You can create golden samples there and distribute them to the factory machines. That allows you to align all stations on the factory floor. It allows you to monitor drifts both in the reference station and in the factory machines. And the prerequisite is that your golden samples are stable. On the right side, the audit concept is outlined. You basically are using traceable calibrated equipment on the factory floor. You are then using an audit source to verify this calibration. That allows you to have the same scale throughout your whole supply chain. It allows traceable measurement down to the factory floor and a traceable check. The prerequisite for this method is the stability of the audit source. Now let's take a look at how these measurement instruments are applied to measure specific characteristics of displays. These applications will help us quantify display output, detect defects, and characterize overall display performance.
There are several display characteristics that can be measured to ensure display's visual performance. We will start with identifying random defects, including mirror and other artifacts. Various types of defects are commonly seen through the display panel supply chain. A mirror or blemish presents itself as a bright or dark local area on the active region of the display. Bright or dark dots can be caused by defective pixels or contamination. Bright or dark lines are also common due to electrical failures in the pixel array. Mirror can take many forms and generally appears as bright or dark blobs in the display area. There are many known causes for this type of common issue which vary across display technologies. Different manufacturing problems will lead to different types of mirror. To meet requirements, each type needs to be specifically characterized and quantified with an analysis specific to the issue. Mirror can be introduced in any stage of the display manufacturing supply chain. Common causes include mechanical stress, embedded contaminants, air bubbles, polarizer non-uniformity, or light leaked from the waveguides along the edge emitters, among many others. Dot defects are the result of the electrical failure of a specific pixel or cluster of pixels. They can also be introduced by embedded contaminants in the layers of the display material. They may only appear when specific solid color patterns are displayed, depending on the cause. They can also appear as bright or dark dots. When measuring dot defects, it's important to utilize various techniques that distinguish between embedded particles, defective pixels, or surface contamination that can be cleaned away. Line defects are almost always caused by an electrical failure of the video drive electronics and manifest as single or groups of horizontal or vertical pixel lines. Again, these may only appear in a single solid color pattern or multiple patterns. Line and dot defects can be caused by several issues during manufacture and assembly of the display panel. For dot defects, these are typically dead or stuck-on display pixels, small particles or dust trapped in display layers, micro scratches on films, micro blemishes in glass. For line defects, these causes are often due to issues with the various electrical components and circuits that drive the pixel array. To identify random defects like Mura, lines, and dots in a display, the measurement system should be able to evaluate a complete picture of the entire active area of the display. Relative non-uniformities and absolute color and uniformity differences should be considered. Adequate detection relies on a sufficient level of imaging resolution to detect defects of all relevant sizes. Smaller size defects or distinguishing subtle differences between adjacent pixels requires a measurement resolution often much larger than the resolution of the pixel array being analyzed. Finally, a measurement needs to be prepared for analysis. This includes cropping and aligning the measurement to the active display area and removing aliasing effect of moire. When we image a display, the orientation angle is not always perfect, and we are not always filling our imaging system's field of view exactly with the display area. Generally, we will capture some background elements like the bezel around the display or elements of the measurement environment. Isolating, orienting, and presenting the display in a consistent manner for analysis enables repeatable and reproducible results. Image preparation includes this kind of alignment and cropping of the active area first to ensure we are applying analysis in exactly the right place. Moire is an aliasing effect caused by the dissimilar pixel arrays of the display and the imaging system's sensor. Because there are small gaps between the pixel of both the display and the sensor, those gaps can be imaged on the pixel of the sensor and appear as lines of various spatial frequencies in the image. These aliasing effects will make proper measurement analysis impossible unless mitigated. To remove the effect of moire, image processing can be applied after image capture and prior to image analysis. A moire removing technique like that applied in the lower right image shows that aliasing can be removed while still maintaining image details sufficiently to identify a single pixel defect. In some cases, moire is removed by defocusing the measurement system, but this effectively reduces the measurement system resolution and can result in the loss of detail necessary to identify small defects with accuracy. Image processing techniques that isolate moire effect for removal therefore offer significant advantage for display metrology. Now that we have captured a cropped and clear image of the display, we can begin to perform analysis. First, we'll discuss Mura analysis. There are 4 basic steps to a Mura analysis process. Step 1, measurement image. Capture a measurement to evaluate luminance differences in the display. Display often have a slowly varying, a low frequency gradient that must be filtered out to detect the smaller gradients. In example, the Mura defects. Step 2, local contrast image. Once low frequency gradients and or noise and moire are filtered from the measurement image, a local contrast measurement can be calculated by generating a smooth reference image, then subtracting and dividing the filtered measurement by this reference. Large positive or negative regions of values indicates the presence of Mura. Step 3, J&D analysis. Optionally, apply analysis algorithms that use a model of human visual sensitivity to identify and rank defects in the local contrast image. Step 4, weigh Mura defects. Apply various methods to weigh and filter Mura to identify different types of Muras by size, shape, quantity, location, and other factors. Mura can be measured, reported, or excluded using various statistical techniques. The magnitude of the contrast, bright or dark, the shape or circularity, size, surrounding defects, location, and color can all be used as criteria filters for an analysis. There is an optional analysis technique applied in software that provides a reliable method of Mura detection and grading based on human perception. Just noticeable difference, or JND, is the amount of difference necessary for a Mura to be apparent to the average human observer. The JND algorithm incorporates a simple model of human visual sensitivity to spatial contrast. Some examples are the Spatial Standard Observer, or SSO, model from NASA, and SEMU from the semi-standards. Some factors that are included in this model are spatial frequency, orientation, and the observer's expected distance from the display being viewed. A JND algorithm can be applied for display metrology and is useful for evaluation of Mura severity. The JND scale is defined so that a JND difference of 1 would be statistically just noticeable by an observer. On an absolute scale, a JND value of 0 represents no visible spatial contrast, and an absolute JND value of 1 represents the first noticeable spatial contrast. This scale allows for the quantification of display defects. This series of images shows a JND analysis being performed to identify Mura in a display. In this image, we see a display measurement with gradients near the edges of the display and 2 Mura defects near the center. The Mura at the center are barely noticeable in the raw measurement image. Here, the local contrast measurement of the display image clearly shows the Mura at the center of the screen. Some artifacts like light leakage and dark spots at the edge of the display are also visible. This analysis highlights Mura that were barely visible in the original image. When converted into the JND scale, it's clear that the 2 spots in the center of the display and some areas along the bottom have a JND values greater than 1, the threshold for being just noticeable. The speckled area across most of the display represents JND values of about 0.55 or lower and could be accepted or rejected based on pass-fail tolerances set in software by the manufacturer. Here is a series of measurement and analysis images that show how JND is used to evaluate Mura on a black pattern on a display. First, an image is captured. Then we apply the previous described analysis techniques to detect and quantify defects that would be noticeable to a human observer. These results can be used to pass-fail or grade the display based on Mura type or severity. Lastly, we can visualize these defects in a local contrast analysis image, which could be saved from the software for reporting or later use. In a fully automated display inspection process, a manufacturer can use JND and other analysis functions to determine acceptable types and severities of Mura for pass-fail. The process entails 1. Each type of Mura is isolated and identified. 2. Each instance of Mura is scored based on severity. 3. Manufacturer tolerances are applied to pass or fail each display based on the type or severity of Mura found in each display. Much like Mura, we use method of local contrast and local gradient analysis to detect dot and line defects. However, unlike Mura, dot and line defects are characterized by very specific geometric properties, size, length, eccentricity, and orientation, typical for lines, horizontal or vertical. Pass-fail decisions regarding dot and line defects are based on photometric properties like contrast or absolute value, spatial properties like size, number, and location. As mentioned earlier in this section, moire removal imaging processing is particularly important for dot and line defects because they are so small and thin. Moire itself will obscure small details from the measurement image and therefore must be removed. In-focus measurement is highly recommended for dot and line analysis, and the moire removal method should accommodate this. The task of pixel level measurement is to ensure precise quantification of light and color for each pixel. As the resolution of display increases and new technologies are introduced, measurement method must evolve to ensure the continuous measurement quality and accuracy. The goal of pixel level measurements is to measure the output of each pixel or subpixel in a display to record its luminance and color value. For measurement systems, there is one dominant challenge to overcome in this process, which is being able to precisely isolate each pixel, even subpixel, as a distinct region of interest for accurate measurement. For this, various registration methods are used that can eliminate or minimize the crosstalk between pixels. The optimal registration method will ensure we are measuring the exact output value of each pixel, that we can do this with high accuracy over each pixel in the display, and that the same pixel level accuracy is present from display to display. Accuracy and repeatability of the measurement are a must. In these images, the large connected bright blue area are display pixels, while the small squares are the imaging system's sensor pixels. For pixel level measurement, we want to sufficiently isolate each pixel, that is, create a registration area or region of interest around each pixel. Correctly capture and report the output of each pixel's luminance and or chromaticity. In other words, accurately measure each pixel. As with pixel defect detection, pixel level measurement is only accomplished using an image-based measurement system. Such a system can use contextual data to determine the limits and position of each pixel and calculate values for multiple pixels in a display at once. Registration method will apply regions of interest around each pixel, shown with the green circle in this example. There are a couple of registration methods that can be used to set these ROIs with varying degree of accuracy. The first registration method we'll call the fixed grid method. This method literally creates a grid of ROI based on certain fundamental display characteristics and attempts to best align this grid with the display pixel array. The benefit of this method is that the software processing is quite simple. There's not a lot of complex computation. Once the grid is set, it's set. However, the obvious disadvantage is that there is not much tolerance for misalignment of the display and imaging system. These elements must remain extremely well aligned and not be moved or adjusted so that the display pixel do not even fall partly outside of the ROI defined by the grid. The second, more robust and accurate method of pixel registration is using active registration. In this method, there is some image processing that allows us to more dynamically set regions of interest per pixel based on each pixel's location. This method tolerates much more flexibility in the alignment of the imaging system and the display. However, there's a lot more computing power necessary, as the image processing is more difficult than a fixed grid registration. The method must be able to account for defect pixel that could be considered a risk of registration error. Further, more advanced shapes of the display, like rounded corners, cutouts for other device components, etc., demands a very flexible and robust pixel registration. Our optimal registration method should also eliminate crosstalk between pixels as much as possible. Crosstalk is when light from neighboring pixels impacts the measurement of the pixel in question. Since the spacing between the pixels are very small, it is extremely important that we accurately define the limits of each pixel so as not to have one pixel's output influence other pixels' measurement value. Eliminating crosstalk between pixels in a measurement image requires optimizing a few key elements: the resolution, the focus, and straight light control. Resolution of the imaging system is key to eliminating crosstalk between pixels. The data here shows a measurement of pixels on a smartphone display. We are zoomed in here to show the detailed pixel. Here we are getting 3x3 sensor pixel per single display pixel. Looking at the image to the left, we can see that each pixel display has very limited visual detail. The cross-section to the right shows luminance across a few pixels. The contrast between each pixel and the background is low, with high risk of crosstalk in measurement from one display pixel to the next. Contrast of each pixel could be affected at this resolution, limiting measurement accuracy. However, 3x3 sensor pixel per display pixel may be just adequate in certain measurement scenarios. With a higher resolution sensor, we can acquire more precise pixel detail and increase the chance that our measurements' accuracy will be consistent from case to case. In this image, we have captured the same smartphone pixel using a system that provides us with a 6x6 sensor pixels per single display pixel. This is much more visual detail in the measurements on the left, and we can now pinpoint the spatial location of the luminous display pixel with 1 sensor pixel precision. The cross-section shows that the much higher contrast with the background and the reduced crosstalk, thus significantly improving the accuracy of each individual display pixel measurement. Enough resolution can be provided in several ways. Each has advantages and disadvantages. We will review these in detail as we discuss each method in the next few slides. So we have testing in sections, space pixel measurements, high resolution single image measurement. The first method to optimize resolution in pixel registration is testing in sections. This can be done using standard optics, applying our full sensor resolution over a smaller area of the display. This increases our measurement resolution per display pixel. Using a microscope lens, we can also zoom in a section of the display. This method multiplies the effective resolution of the imaging system per pixel. The method works extremely well when characterizing individual light-emitting elements like subpixels or micro-LED. However, because we only capture parts of the display at a time, a complete measurement of the display with all its pixels will require using a translation stage to move display and the imager in relation to each other. There will also be a lot of processing required to combine the individual images of each display section into a single image while maintaining accurate pixel location. This method is the highest resolution but slowest of our measurement approaches. The second method to optimize resolution is spaced pixel measurements. Like testing in sections, this method increases the effective resolution of the measurement so we can apply more image sensor pixel across each display pixel. A slight defocus can be applied. Unlike testing in sections, however, this method captures the full display area in every measurement. During spaced pixel measurement, a series of dot matrix patterns illuminate subsets of display pixels at a time. Different patterns illuminate different subsets of pixels until values have been acquired for all pixels in the display. Please remark that no translation is needed for this method. A synthetic image, as shown on the lower right, is produced from the combination of all measurement images. In the synthetic image, measurement to display pixel resolution is 1:1, So each dot seen in the image on the lower right is reporting the value of one display pixels. A false color scale is used to represent luminance, with cool colors being darker and warm colors being brighter. The synthetic measurement image offers a very compact format for reporting the measured value for each display pixel. The benefit of this method is that the resolution is maximized for each pixel because only a limited number of neighboring pixels are measured at once across the available image sensor resolution. The drawback is that because many measurement images are needed, the cycle time for a complete display measurement can be too long. This may not be adequate for certain inline display test processes. The last method of optimizing resolution for pixel registration is high-resolution sensors. This method captures a single image measurement of all the pixels in the display at once. The higher the resolution, the more sensor pixels per display pixel, the more accurate the registration. The optics for very high-resolution images must be of extreme high quality, and the sheer amount of data captured, processed, communicated, and stored will require a large amount of computing power. As displays and measurement systems trend higher in resolution, it is likely that we will see further optimization of these critical components. In the meantime, using standard imaging resolutions, novel imaging processing techniques, and analysis algorithms have been shown to improve measurement accuracy for relatively low sensor-to-display resolution scenarios. In addition to optimizing resolution, optimizing focus across the entire measurement image plays a significant role in the accuracy and repeatability of pixel registration and for eliminating crosstalk between display pixels. The measurements shown here illustrate this. On the left, focus of the imaging system is uniform across the measurement area. We can see that we are able to clearly distinguish the pixels in the display, both in the center and at the corner of the measurement area. On the right, focus uniformity of the imaging system is poor, resulting in large differences in image quality from center to corner. It is seen that at the corner, the resolution is so poor that the pixels bleeding into each other and makes it impossible to measure the individual pixels. Stray light is unwanted light that reaches the image sensor due to reflections, light scatter in the imaging system. This light can introduce ghost images or revealing luminance on the image sensor. It reduces clarity between light and dark areas and effectively reduces pixel definition. Failure to control stray light has a big impact on the system's ability to measure accurate contrast values, which are necessary for distinguishing the area of a single pixel or subpixel. In this example, two imaging systems, same sensor, are compared for their ability to control stray light. On the left, we have the measurement image where a high contrast is established as a dark spot on a very bright background. On the right, the cross-section plots records the luminance measurement of the two imaging systems as measured along the red line in the left-hand measurement image. On the orange line in the plot, we see excellent stray light control from System A with clear definition at the transition from low to high luminance from the black to the white areas of the image. Looking at the gray line on the plot, we see poor stray light control from System B with luminance values imprecisely measured, especially in the center black area. Were this a pixel level measurement in a display, System A would be preferred for pixel registration, ensuring accurate definition of the pixel region of interest and eliminating crosstalk between closely spaced pixels. If we can calculate the luminance and color value at the pixel level, we can then apply this data to remove pixel-to-pixel discrepancies, variation that cause visible non-uniformity. This is prevalent in displays with independently emissive pixel elements like OLEDs and micro-LED-based display like Mini and micro-LED. We calibrate out this non-uniformity by calculating the differences in values from pixel to pixel and creating correction factors to adjust the signal of each pixel to a uniform output. For each RGB pixel, correction can be applied using this method. Measure the original gray value for each pixel, create a correction factor via a lookup table, mathematical function, etc. Apply this factor to correct the gray value for each pixel. This process of pixel-level uniformity correction is also called demurrer because it effectively removes pixel-level murrer from the display. It is used to demurrer the display. In these images, we show at the bottom an illustration of correction being applied to a different pixel position to adjust the output value at various gray levels. On the right side, this is a composite image of two real measurement examples of demurrer of an OLED smartphone display. The top portion is before demurrer and the bottom portion is after demurrer is applied.
We can take a step back from the pixel level for a moment and talk about broad display uniformity, which has similarities with the Murrer evaluation, but its own unique considerations. When talking about lateral variations, we can look at very different scales. Jens just showed us pixel level defects, hence on a very short scale. We come now to uniformity, which analyzes long distance variations over the display. Uniformity can be measured with a few sample points, but of course the analysis can also be derived from a high-resolution image. The boundaries between Murrer and uniformity analysis are soft. Here are some suitable measurement systems to analyze uniformity. As I said, uniformity can be measured with a few points, for example with 9. That allows to use photodiode-based photometers like the example for a spot meter. There can be even 9 spot meters measuring at the same time, resulting in a very fast acquisition time. Or a Spectroradiometer can be used, or a scanning system can be used instead. Also very conveniently, uniformity can be derived from an imaging light measurement device, as depicted here. They allow very high resolution. It can be either a monochromatic device or a color version to analyze uniformity both in luminance and color. A special kind of imaging device is a spectrally enhanced imaging system. It combines the accuracy of a spectroradiometer with the versatile use of an imaging device. Spectrum and image results are then combined to a very accurate 2D image. That can be achieved either with a precise XYZ filter on a wheel or in a one-shot solution with a biopattern camera. Several evaluation methods for uniformity with imaging devices are outlined here. The most intuitive one is to simulate a number of spot meters. A popular number is, for example, a grid of 5 to 7 spots. Normal spots create voids where the algorithm is not sensitive. That can be cured by the example of a grid of rectangular spot meters. Or closely related is the method to use a high degree of binning, or to use a floating average to low pass the image. With all methods, in the end, you want to compare minimum and maximum values to result in a value for uniformity. Here is an example of a 9-point uniformity measurement. In this example, the DUT is an AR/VR goggle. You can select the pattern to do the uniformity analysis. Typically is to use the 3 primary colors and white and maybe some gray levels. Uniformity is typically evaluated for both luminance and color. An advanced method to look at uniformity errors is to use the gradient method. That is because the eye is more sensitive to rapid changes rather than to smooth gradients. Hence, a non-uniformity of a few percent over the display might look okay, but if the change occurs, for example, at the edge, it is disturbing. In older displays, such blemishes were often observed, especially in the dark state of LCDs. With the gradient method, their visibility to the observer can be easily quantified and quality assured. Here is a workflow and different ways to look at the displays. On the left, you have the original defect with a blob. In false color, you see both the blob but also non-uniformity of the display. With a gradient filter, the blob is separated, and with a binary image, position and size can be evaluated and depicted. Display metrology and quality assurance typically assumes perpendicular measurements. With an imaging colorimeter, the display is observed from a finite vantage point. How can this be tackled? For small displays, this is easy. You can use a narrow field of view, and the effects of the finite vantage points are negligible. Of course, you can use multiple devices, as in the picture here, to ensure perpendicular views. Or you can scan the display. It is most accurate, but comes on cost and higher measurement time. And finally, you can use a correction method if you need both large field of view and a high throughput. That might be necessary for large TVs and theater-like entertainment systems. For practical use, you might need a wide-angle lens. With some reference measurements, you can create a multi-point correction. The approach is outlined here. We measure a grid of spots in a scanning approach. That gives a matrix of references for the three stimulus values. With an overlay with an image taken from the finite vantage point, you can create correction values for these spots. With an interpolation, the image can be corrected accordingly. Since this is only a small correction, it typically can be applied to all DOTs of the same kind. For the absolute truth on uniformity, a scanner is the right choice. You can eliminate or separate influences of directional and lateral properties. You eliminate device-to-device variations, as in the approach with multiple detectors, and you eliminate potential effects on flat field calibration, vignetting, or other imaging artifacts. Hence, with a positioner or goniometer, you can characterize and potentially eliminate artifacts. Here is a compilation of critical aspects when selecting a light measurement device. It is a commented list of the criteria according to a publication from the DIN. On the left side, you have the items, for example, spectral matching. This is especially important if you have filtered detectors, but you can also use a spectral radiometer. Sensitivity to UV and infrared is not very significant. That is because displays usually don't emit in this range. Linearity, however, is a major concern, especially for OLED devices which have a very high dynamic range. Straylight has two aspects, the one within the setup and the other one within the light measurement device. That is for both a spectrometer and for a camera. The next three aspects have a moderate significance. So polarization errors, focusing errors, and temporal effects should be characterized both by the light measurement device and the setup, but usually don't impact too much. That's different for the temporal modulation, especially for OLED devices, which are strongly PMW modulated. Therefore, synchronization is needed. And the largest impact has the calibration error. As we have seen, display quality is dependent on a number of factors, including the angle at which the display is viewed. In many applications, displays are not viewed straight on. Measuring based on the directional view must help us to understand how a display visual quality changing as the display is viewed at an increasing angle. As we had before, from a finite vantage point, the display is always seen under an angle. At small angles, these effects are small. However, with the trend for AR/VR goggles, head-mounted devices, and near-eye displays, the topic gets a completely new dimension. The direction of observation is specified in polar angles. Typically, theta is used for the inclination, and phi is used for the rotational angle. Here is an example for the viewing direction of an LCD. In the white state, a moderate drop of luminance is observed in inclination. Rotation is not an issue. However, in the black state, rotation is very significant, and the switch off at certain directions is impaired. In consequence, the contrast is highly reduced in these directions. The impact on the observer is a loss of perception and impaired image quality. One way to analyze the variation with viewing direction is a goniometer. It features a motorized scanning of the viewing cone. Several detectors can be used, for example a photometer, a spectroradiometer, or even an imaging device. Extremely high mechanical precision is needed to achieve repeatable and meaningful results. The measurement is rather slow, but gives a high precision result and good control over all parameters. I have compiled a few slides with examples. Here LCD and OLED is compared in luminance. The OLED is more symmetric in rotation, but the luminance drop is similar to LCD. When looking at chromaticity, here the OLED device shows a significantly higher impact on the inclination than the LCD. To dig into this aspect more closely, we have here some profiles for an active matrix OLED display, both in luminance and color. The luminance show a significant drop, but is rather smooth. The impact on chromaticity is much more severe. It is typical to have a quite large color shift for OLED displays, and the ripples you can see in the profiles are characteristic. It is an engineered parameter which needs to be quality controlled. Here is a study on 8 different OLED products from 6 different brands. You can see that they are significantly different in angular behavior. Some manufacturers seem to accept a higher shift probably in order to increase color gamut and efficiency. Others limit the impact on a certain value. You can see with the LCD reference that the state-of-art LCD technology surpasses OLED easily in this aspect. For production control, you need faster methods than a goniometer. Hence, there are other ways to measure the angular behavior. Here is an example of a conoscopic lens. It essentially is a lens used in its focal point. Thereby, it converts the angular characteristics onto an imaging device. It allows to measure the directional luminance dependence in one shot. You can even pair it with a filter wheel camera, so you can also characterize the chromaticity error on viewing angle. Here is an example of such a device. And here is a comparison with a goniometer. You can see a good agreement between scanning methods and the use of a conoscopic lens. A further aspect is the display seen under ambient illumination. This property is a bit related due to its strong dependence on viewing direction. Ambient lighting can be extremely complex. You have usually bright, highly directional sources like the sun, but there is also diffuse light coming from everywhere, for example in an office. Hence, for display characterization under ambient illumination, an accurate description of the conditions is essential. That includes geometrical aspects, spectral power distribution, and it might include dynamic aspects. And of course, also the detector configurations needs to be specified. An example of an implementation of such a setup is shown here. There is a diffuse light source with a slit in order to measure through the slit. An additional collimated light source simulates something like the sun. More scenarios can be created. Typical reflections from a point light source are shown here. On the old-style display to the right, no optimization has been done. Hence, the glass surface creates a sharp specular reflection. To the left, you see a monitor. Commonly used is a scattering anti-reflection surface. This is a mean to avoid annoying ghost images from the environment. Modern mobile devices feature typically a multi-layer anti-reflection coating. Together with a complex structure for touch and other functions, it often results in a structured star-like reflection. The reflection closely around the specular reflection is called haze. With a setup for ambient illumination, a full characterization of the point spread function is feasible. The four examples here show results. Top left, a mirror-like image with some diffraction from the pixel matrix is seen. Top right, haze with a controlled specular peaks is displayed. And bottom, haze with small or no specular peaks is shown.
Okay, the last display characteristic we'll discuss requires evaluation of a display as its output changes over time. The temporal characteristics of flicker require unique measurement functions and equipment to ensure the display quality at all times. Flicker is one of the major artifacts in display quality, which is defined as visible change in the brightness of a light source. Flicker is not only annoying, but also causes eye strain, migraine, and several other health issues, which lead to customer complaint. Also, recently, a lot of mobile displays use low refresh rate, so flicker could be more noticeable in such case. So many display manufacturers has been trying their best to reduce the flicker. For example, DC dimming is one of the ways to make flicker invisible. With DC dimming technology, theoretically flicker could be totally invisible. However, in reality, DC dimming is not major technique because it is simply challenging to implement DC dimming without several issues such as color shift. So most of smartphone displays are not DC dimming, but still using PWM to dim the brightness. DC dimming aside, you can still do many things such as improving TFT design or changing pixel driving structure or fine-tuning Vcom for LCD. However, there are still flicker issues existing in the market. Flicker is visible change in a brightness. So if it's invisible, we should have no problem with it. Which means you want to determine if it's visible or invisible. However, how we sense something is up to individuals. So we need to quantify flicker so that we can give us a threshold. In order to quantify flicker, the key factor is temporal contrast sensitivity function, which is called TCSF. TCSF represents people's sensitivity to modulated light at various frequencies. So TCSF can be used to determine flicker visibility. The graph on the left side represents one of the TCSF curves published in a paper. In this graph, horizontal axis represents frequency, while vertical axis represents sensitivity. In this graph, you can see that we are insensitive to higher frequency components. Considering the concept of the TCSF, we can make flicker analysis much easier. Let's see the right picture as an example, which represents time domain waveform signal. In this figure, lower frequency component is highlighted by red circle, and higher frequency is highlighted by blue circle. Based on TCSF, you can say that lower frequency component corresponding to gradual slope is more visible to human eye. On the other hand, high frequency component corresponding to sharp signal transition is almost invisible. So in order to reduce flicker, now you have to focus on this lower frequency component. Also, you might be able to ignore the higher frequency component. TCSF can be used for such analysis. This TCSF curve is different in different papers, so you need to carefully choose which one to use. One famous feature of the TCSF is its depending on luminance level. So ideally, flicker visibility evaluation should be done with high response luminance meter. TCSF has been studied by several scientists in the past decade. One unique feature of TCSF is that it depends on luminance level. In this graph, when luminance level goes lower, the TCSF could be shifted to bottom left. So we see reduction in peak sensitivity and critical frequency that can be noticeable. On the other hand, when luminance level goes higher, the TCSF could be shifted to top right. So peak sensitivity and critical frequency increase. If you want to specify the luminance level, then you should use different TCSF. I'm done with TCSF now, so let's move on to the next topic. In this slide, I'd like to explain how waveform could be different in different display technologies. The waveform characteristic shown in this slide is just a typical example, so it could be different in your own display. First of all, LCD. DC biased flicker is one of the famous LCD artifacts. This is caused by residual Wickham offset, so its positive and negative frame could have different brightness. You can compensate this by fine-tuning Wickham level, but in many cases you can still see the flicker when you display a specific image pattern on the screen. When it comes to OLED, there's no Wickham, so there's no DC biased flicker. Instead, you might see a flicker caused by current leakage on the TFT. Also, you can often see the PWM in between each frame. My point is that driving method and waveform shape could be different across different display technologies. In addition, the cause of the flicker could be also different. Not only electrical design, but also optical viewpoint needs to be taken into account. Recently, variable refresh rate, so-called VRR, is becoming a new standard. This is how it works. When you watch static contents such as static picture or book, we don't need high refresh rate, so the screen automatically lowers the refresh rate to save power consumption. On the other hand, when you watch motion contents such as video game, then the screen automatically switches to higher refresh rate so that you can enjoy more smooth picture. This means that the VRR screen is switchable between high and low refresh rate depending on contents. As I mentioned, lower refresh rate causes more visible flicker according to TCSF. LTPO technology has been coming up recently, replacing conventional LTPS. This LTPO technology enables low flicker even with low refresh rate thanks to its law of current. When it comes to lower refresh rate, LTPS has so high leak current that causes visible flicker. On the other hand, LTPO has low leak current, so you could refrain flicker even with low refresh rate. Using measuring instruments for flicker measurement could be also challenging because we need to take many things into consideration. For example, sampling rate and sampling durations are important parameters, that we need to set up in advance. Sampling rate should be high enough to nicely capture the highest and lowest frequency of waveform signal. But it doesn't mean higher sampling rate is always better than lower sampling rate, because higher sampling rate leads to less light sensitivity that affects signal quality. Sampling duration is also very important because it has an impact on synchronization with periodic waveform and the frequency resolution in FFT analysis. Also, other specifications like linearity and resolution could be also very important. You need to care about those when performing flicker evaluation. Let's dive into more details of flicker computation. Flicker metric is used to evaluate flicker in accordance with human visual system. So we can quantify flicker and determine if it's visible or not. I explained something about TCSF, but TCSF is just a part of algorithm, so which has to be integrated into flicker metric. There are many types of flicker metric, such as JETA, FMA, and IEC, and so on. But there's no perfect flicker metric that can be applied to all applications and all type of display, because waveform could be different across different type of display. So we might need to use different flicker metric in different applications, or maybe we need to develop our own algorithm by tuning it. So you have to evaluate the flicker metric upfront and see whether or not it has a proper correlation with human visual system. You don't have to stick with existing flicker metric. Here is an introduction of one of the flicker metric. This is a FMA flicker. FMA flicker is a quite simple method. What you need to do is just taking maximum and minimum luminance level from signal waveform and then calculate the contrast. This is very simple and easy to calculate, but normally it requires a low-pass filter to filter high-frequency outlier. This one is JETA method. JETA method is based on frequency domain calculations. As a first step, you need to apply Fourier transform to signal waveform. It can be FFT or DFT techniques. Then you can get frequency domain spectrum and apply TCSF to the frequency component. This TCSF weighting factor is applied to compensate human visual system. And next step, we take the ratio of DC and maximum AC component and take the log scale so that it can be converted to decibel unit of flicker amplitude. This one is more stable than FMA flicker, but it takes some computational power because we need FFT or DFT techniques. Also, this metric only takes a single frequency component. For example, in this page in this FFT spectrum, we only take 20 Hz frequency component into account, so 50 Hz will be ignored. This might be okay for some applications, but not okay for some cases. So apparently, JETA flicker is not a perfect metric, and we should select a proper flicker metric depending on your use case. Okay, so this is the summary. For instrument setup, measurement parameters must be properly set. And we should carefully pick and use proper flicker metric, otherwise the result doesn't make any sense. And if you can correctly set up instrument parameters and flicker metric, then you should be able to quantify flicker. This is an advanced way of evaluation of flicker. It is two-dimensional flicker distribution. Actually, some type of displays, such as LCD, could have flicker distribution like this picture. This is just a typical example, but actual measurement result. In this picture, you see the corner or edge of the display has more visible flicker, while the center of the screen has less visible flicker. This is because there's uneven material distribution. For this type of distribution, spot flicker meter is not sufficient to accurately understand the characteristic. The last section of today's course will cover emerging display types and integrations and how measurement methods have been adapted to continue to ensure quality for these new devices.
Let's start with discussion of mini LEDs, micro LEDs, and micro OLED. These tiny emissive elements are greatly improving display performance capabilities and are challenging metrology systems to measure output on an increasingly small scale. Here are some motivations why the industry is investing a lot in micro LEDs. They allow even higher color gamut than its organic counterpart. Contrast can be at least as high as with OLED, and the peak brightness is superior to everything else. We come to resolutions and pixel sizes in more detail, but they can be extremely high, and they feature a wide viewing angle. Usually there is also efficiency mentioned. It is for sure a motivation, but to reach high efficiency with small LEDs is not yet solved. But the main issue remains the manufacturability and at reasonable costs. That include the challenge for quality control, yield, and repair. The definition when a LED can be called micro LED is not so clear. LED Insight has recently dared a definition that might be adapted in the industry. Obviously, the size is one aspect, but they also see that a real micro LED can only be achieved with the sapphire substrate removed. Hence, they use this to distinguish between mini and micro LEDs. I think a further important distinction can be made by integrated devices and assembled devices. In the integrated device, you have many LEDs, up to a whole display, on the wafer. It is created with semiconductor processing means. Examples of integrated devices include white devices, like they are used in headlight projectors. It also includes monochrome devices. They can then be optically combined to a colored display. Or complete RGB devices. They are often micro OLED, but also inorganic versions have been demonstrated. For assembled devices, backlight units are early adopters. Also, RGB versions are available for professional video walls, luxury screens, and also for watches. Here is the landscape of use cases for micro LEDs. It outlines the assembled devices to the left and the integrated approach to the right. Top are the large-scale LEDs, which are already readily available. Going further down, the LEDs are getting increasingly small, and products are not yet very mature. LED tiles for video walls are already quite well established. Mini LEDs for backlight units are boosting the dynamic of LCD with the full array local dimming technology. That boosts the performance of LCD again to keep up with OLED. They are on the market and announced to gain market. And with small displays like used in watches, the assembly is already successful. On the right side, adaptive lighting for cars is the driver for the ultra-high brightness structured LEDs. With increasing pixel numbers, they can also be used in projectors. The ultimate market for integrated microdisplays is forecasted for augmented reality products. The battle is ongoing. Which technology will make it? Shall it be organic or inorganic LEDs? A combination of colors already on the display, or should the colors be combined in the optical elements of the goggle? Here is a colorimetric motivation outlined. Why to use micro-LEDs? Micro-LEDs have even less bandwidth than OLED, and much less than LCD, of course. That can be seen in the spectrum below. Blue is quite similar, red and green are narrower than OLED. In green it is not so obvious, but if you look at the corresponding gamut, it becomes clear that it is considerably increasing the gamut. However, that also increases the challenge to measure the display colors accurately. Here the challenge of the narrow spectrum is explained. An important parameter for filter-based measurement systems is a so-called f1 prime number. It is a measure for the deviation of the physical sensitivity curve to the tabulated V lambda curve. Similar approach can be used for other filters. For highest class photometers, a f1 prime below 1.5% is expected. A publication from CIE plots here the f1 prime against errors or correction factors for LED spectrum of many different colors. It shows that for narrow spectra, the error can become significant even with a high quality filter match. Concretely, it is a warning that f1 prime is not valid as an error estimate. Error can be much larger. How to solve? Well, use better filters. However, that has some limitations at one point. A second option is to use custom calibrations or advanced calibration schemes. And last but not least, use the Spectroradiometer. A second challenge is the sheer number of LEDs. For example, on an assembled display, a subpixel number of several millions is quite normal. 4K and 8K monitors might go even to tens of millions of subpixels. You can use ultra-high resolution equipment. An example is shown on the right side with the Google phone Pixel 3. It is measured at the ultra-high resolution of 600 megapixel. Or you can use stitching of several cameras, or you can scan the object with a lower resolution system and stitch afterwards. Also in an earlier manufacturing status, on the wafer, the number is challenging. Before assembling a device, an individual test of the LED would be beneficial. Current quality control on wafer level is not solved to full satisfaction. Approaches with high parallel testing with probe cards or even with optical excitations are tested. Sequential testing at high speed is the brute force method. But current test method either contribute significantly to manufacturing speed and cost, or the test scope needs to be limited below needs. A partially related challenge is the small size and pitch. That is essentially true for integrated devices, both on organic and inorganic LEDs. Pixel size and separation between pixels below 1 micron have been demonstrated. It is extremely challenging to the optical system to resolve such structure, especially for large field of view. Several technologies are offered and recommended here. In one approach, the field of view can be reduced, and moving stitching is used to characterize the full display. A bit smarter is a technique to address diluted pattern on the display. For example, only every third LED lights up. Then you measure in several sequential steps. Last but not least, for some DOTs, not for the extreme ones, it is fastest and best to use very high resolution camera with an excellent optic in the macro or even microscopic range. An example is shown here with a monochrome micro LED integrated green display. A full analysis can be made in one shot. Challenging for display quality is also the non-linearity of micro LEDs. You see here 5 patterns of the same display in the same position. Note the difference in the white and dark gray pattern. On white, the pattern looks rather smooth to the extent of visual evaluation. At gray level 5, a non-uniform pattern is quite obvious. That means that LEDs are acting differently at small driving currents. For measurement, it poses the challenge of accurate measurements even at very low luminance levels. Here is an example of an OLED microdisplay. It is a full HD display made of micro OLEDs. It is the research result from the group of Dr. Vogel at Fraunhofer. The measurement is taken with a 2x magnification. Here only the green channel is used. And here you see the other color channels, red and blue as well as white. You see that the subpixels can be nicely resolved on individual channels, but on white, subpixels are overlapping and the evaluation becomes difficult. That is at a subpixel level of 5.5 micron. Let's come to a few solutions how to measure such micro LEDs. Of course, the device of choice is an imaging light measurement device. You want to have high resolution and you want to resolve individual pixels. That can be achieved by the use of a microscope lens. It can be used to measure individual LEDs and subpixels. You can use it for offline testing, or you can step over, for example, a wafer. Beneficial is a lens which allows to align the sampling ratio between camera and display. That helps to minimize sampling artifacts. And it can be either a monochrome or a color version for the camera. Some details about micro LED wafer testing and potentially smaller micro LED devices. So we are talking here about DUTs like a watch or a wafer with a naked micro LEDs. A solution can be a spectrally enhanced colorimeter. With the example shown, LEDs down to about 30 microns can be evaluated. The field of view is in the range of a few millimeter up to a few centimeter. Parallel testing makes sense from a few hundred to a few 100,000 LEDs at the same time. A few 100,000 LEDs is typically reached with a watch. On the wafer, one of the main challenges is how to energize the LEDs. The best quality control is achieved with 100% testing, including electrical parameters. For that, a probe card and a corresponding number of current sources is needed. The number of parallel tested LEDs is limited today to a few hundred by the probe cards. Much faster speeds can be achieved by limiting the test scope to optical performance only, hence no testing of the electrical parameters. That is done by UV photoluminescence measurements. Many thousand LEDs can be tested in parallel. Of course, energizing is much easier on integrated or assembled devices. There you can use the integrated drivers. A solution for a wafer testing must be designed for speed. That requires hardware triggering, it requires a single-shot solution, and fast and accurate algorithms. Here another example is shown for full display characterization. Emitter size and pitch can be in the range of 1 micron to a few hundred micron. For variation of the lens, the range for the field of view is quite large. As discussed before, the number of emitters is in the range of a few millions. Also, a spectral enhanced imaging colorimeter can be used, but additionally, an extremely high resolution is needed to sample each display pixel with many camera pixels. And efficient algorithms are needed to work with the generated amount of data.
Another emerging display application enables devices like smartphones to capture images through the display layers. Let's discuss under-display cameras and the important balance between ensuring display quality and camera functionality. In modern smartphones, camera technology is one of the biggest portions of innovation. As you know, there are different types of front camera: notch, hole punch, and under-display camera. Under-display camera has been developed recently and started to be commercialized in the market. Under-display camera is designed to remove a black area on display screen to accommodate camera or sensors in order to enable super high screen-to-body ratio. But there are still many challenges to be overcome in order to have under-display camera more mature technology. As all you know, UDC is hidden underneath display screen. Then we have two big issues: camera image quality and display quality. Here is a simple illustration to show what UDC looks like. Conventional smartphone's front camera is above the display panel, so it can get enough amount of light. However, when UDC is underneath the display screen, so many layers block the light. This light loss results in low quality of pictures. That's why many display manufacturers increasingly try to develop more transparent layers. Another issue is display quality. To increase the transmittance, we might need to change the pixel structure or layer structure, which have an impact on the display quality. Here are some examples of negative artifacts on display quality. First of all, color or luminance difference around UDC area. If pixel structure is different, luminance level and color on UDC area must be different than other area. We need Mura compensation or separate gamma tuning in order to compensate the difference. When it comes to Mura, we might see other visual defects because of two different pixel structures side by side. For example, there could be a line Mura in between UDC and other display area. If you need to drive UDC area at different refresh rate, then flicker also can be a problem. To evaluate UDC characteristic, you need two different solutions: spot type of light measuring device or image-based light measuring device. For flicker and gamma tuning or any time-consuming inspections, spot meter will be recommended. UDC area is normally a few millimeters in diameter, so small spot measurement should be required. For Mura measurement, imaging calorimeter or photometer is required. Because of course, spot meter is not capable of measuring luminance and color distribution around the UDC area. Here's just one example of specific metrology that might be required for UDC characterization. UDC area could have different pixel structure and different gamma. To compensate the difference, individual gamma tuning for both UDC and other area may be needed. In such case, especially Mura around the UDC area is quite important. This is because higher gradient Mura is more noticeable to human eyes, and we are most likely to see the highest gradient Mura near the UDC area. These figures of smartphones in this slide represents an example of how to reduce the Mura artifact. What we propose to do is gamma tuning separately on the both UDC area and normal area. Adding to this, two different tuning points should be adjacent to make flat field around the UDC area. For this application, we may need a customized dual spot meter to measure 2 points as close as possible. Next, we will discuss foldable displays. The measurement requirements for these screens is very complex. There are multiple display layers to consider, which exhibit different changes when folded over time. A complete measurement must take into account the performance of the display itself and the cover window. Foldable smartphone is a smartphone with a folding form factor. We see two different types of foldable smartphone: twin screen type and single screen type. Twin screen type has two separate screens, and the single screen type folds a single big flexible screen. This single screen type can be subdivided into different categories by either horizontally or vertically, in folding or outfolding. Not to mention, the biggest problem with foldable smartphones is cost. it's still expensive as compared to regular smartphones. However, from display measurement perspective, crease and wrinkle could be a problem. A foldable smartphone is made of multiple flexible layers. Cover window is one of the key components to make reliable and beautiful screen. Conventionally, plastic was most commonly used for cover window because of its flexibility. However, plastic is more likely to be less scratch resistance as compared to glass. Also, crease and wrinkle are more likely to appear near the hinge. So recently, glass type of cover window has been developed for foldable smartphones. It is a glass, so it has more scratch resistance, yet still flexible. The glass improves not only scratch resistance, but also crease problem. However, glass is more likely to break due to tensile stress. So we still need a protective film to avoid glass breakage. So, whether plastic or glass, wrinkle has not been resolved. These pictures are actual foldable smartphones with wrinkle on it. Compared with regular tablet or smartphone, we still see some wrinkle. This kind of wrinkle is more likely to appear around hinge because it is the most stressed location. Visibility could change when display is turned on or turned off. So different measurement approach would be needed for each case. When display screen is turned on and emitting light, we can directly measure the mirror with image-based light measuring device. The characterization should be done with just noticeable difference so that we can determine the threshold. These images show that crease can be seen as luminance mirror, and it depends on viewing direction. When screen is turned off, we need an illumination to evaluate crease and wrinkle. Since the display is not emitting light, luminance level is not so important. Instead, it would be important to accurately measure and analyze geometric surface of the screen. For such analysis, image-based light measuring device and high brightness illumination system will be required. The illumination system must be capable of projecting a specific image pattern on the surface of a foldable display, and then the imaging system captures the reflective image for analysis. If the surface of a display has wrinkle on it, the pattern will be distorted, so the wrinkle can be detected and quantified. The whole system setup and algorithm should be well correlated with human visual perception. Here is an actual image of a typical foldable smartphone. We clearly see the image distortion near the hinge, which implies there would be a wrinkle or a crease on it. Image processing techniques is also required to accurately detect the distortion and calculate to what level it is distorted, so that we can determine the pass or fail threshold for the sample.
Another application of display metrology, which is becoming more established these days, is the headset. As devices in AR, VR, and MR continue to develop, new display test equipment and test method must evolve to match their unique characteristics. Here is a rather abridged list of such devices. These are often collectively grouped into extended reality or XR, which includes augmented, virtual, and mixed reality. These headsets can have dramatic variation in optical design, field of view, display technology, resolution and pixel density, opacity, and form factor. For example, the Vive Pro VR headset has a huge field of view of 110 degrees across the horizontal and is entirely enclosed, while the Music AR headset only has 19-degree field of view and can easily be mistaken for a pair of normal glasses. Yet despite these sometimes huge differences, they share many of the primary challenges of characterizing this kind of displays. The optical requirements comes from the fact that XR displays are viewed under circumstances unique to this form factor. Although the projections in XR displays are made to appear focused at a distance, the displays themselves are being viewed very near to the eye. With the viewer's pupil positioned so close to the headset's viewing lens, the viewer's eye becomes part of the optical system, and this must be accounted for in the test setup. These XR displays also frequently encompass very wide field of view and binocular vision to maximize immersion, which can make designing such a system very difficult. And the tight form factor further constrains what test equipment can be used. The primary purpose of display metrology in XR devices is to characterize the entire display and optical system and evaluate their performance as it is perceived by the wearer. This means that metrology system must replicate human eye characteristics within the limitation of the hardware. An XR display metrology system should have optical characteristics that ensure the test system has an aperture which is similar to the human eye, usually around 2 to 5 millimeter. Ensure that test equipment aperture is positioned where the user's pupil would be under normal use, and ensure the field of view of the capturing equipment is sufficient for the device being tested. Traditional imaging systems with a wide-angle lens can capture an appropriate field of view for these XR displays and can have an aperture which can be adjusted to match the required size. The issue with traditional imaging systems, however, is their aperture are designed to be inside of the optical system, severely limiting the ability to position the aperture inside the XR headset and at the same proximity to the display as that of a user's pupil. The resulting measurements will have much of the field of view occluded by the optics of the headset. We can see an example of this knothole effect in the example here to the right, where a lens with a relatively wide field of view has been placed very close to a knothole in a fence, but the view is still blocked because the point at which the field of view converges is still some distance behind the knothole. With a special optical design that positions the lens entrance aperture at the very front end of the lens, it is possible to place our entrance pupil at the location needed in relation to the XR headset. Using the knothole analogy, as the entrance pupil approaches the correct pupil location, the effective field of view expands to the capability of the system. We can now achieve the full field of view of the intended visual experience. Here are some AR/VR test systems that utilize this front-of-lens aperture design to enable imaging of the headset's full field of view within the specific viewing geometries of the headset. Both systems fit within the headset, with the entrance pupil placed close to the viewing lens where a user's eye would be. On the left, we have an optical design that is straight, and on the right, we have a folded periscope design. The optics of an AR/VR display test system require some unique calibrations to ensure accuracy for an image-based measurement. First, the luminance should be corrected using a flat field calibration to achieve a uniform system response over the entire field of view. In the left set of images, we can see the goniometric measured luminance distribution and below an imaging system measured distribution. The two measurements have a very close agreement, both in magnitude and details. Second, wide field of view optics exhibits geometric distortion. See the top right. Calibration and image processing is used to remove the distortion. See bottom right. Further, the distortion calibration enables a precise readout of angular coordinates. These calibrations work together to evaluate the XR display, and standard 2D image analysis function can now be applied to the measurement image to evaluate display performance and appearance. Once a clear and calibrated image of the display is captured by the metrology system, we can apply several analyses to verify display performance. Examples include checking the display for defects such as mirror and line defects. The field of view can be inspected to ensure it meets spec. Warping and distortion in the display can be characterized. Focus uniformity, contrast uniformity, relative MTF can be tested as well. These tests will indicate the individual quality of both the headset display and optics. Here is an example of an analysis of a VR headset display. This field of view analysis calculates the actual field of view of the display as it is seen through the headset and reports the found horizontal, vertical, and diagonal field of view. These measurements can be used to verify there is an occlusion of the XR display and that the projected image has the intended size, that it meets the specifications. A uniformity test is performed by the display sending out the signals to create a uniform luminance and color at all angles. The measurement system takes a measurement and analyzes the luminance and color variation shown. In the example above, the bright region in the upper right corner, along with the overall gradient top to bottom, indicates a poor performing display and would probably be flagged as failing the configured quality criteria. MTF is a common XR display analysis which has benefit for ensuring the clarity and sharpness of a virtual image seen by the user through the headset. The challenge is isolating the appropriate data for the MTF evaluation. Images here shows two methods for testing MTF in XR displays. It is important to note that because we are using an imaging system which itself has an MTF, we can only measure relative MTF. This is still very useful when comparing prototypes or in production to ensure the optical system of the XR device is within tolerances. One of the best known methods for MTF measurement is the slanted edge, shown on the left. Here we measure a bright box with a slanted edge. Measurement values across the edge gives us the line spread function in the top left plot, and then the Fourier transform of that becomes the MTF plot shown on the bottom left. In theory, this slanted edge method works quite well. The issue is that we are using a pixelated sensor to measure a pixelated display, so we need to remove artifacts caused by competing pixel geometries. Here the resolution of the measurement system is so high, we measure some of the contrast between the separated pixel of the XR display. We want to characterize the separation between the dark and light region in the test image, but we are getting interference from the pixelation of the display pixels themselves, which cause a false MTF spike, which should be ignored. A line spread method addresses this as shown on the right. Instead of displaying an illuminated box for our test image, we are displaying a discrete line of pixels. The measurement system characterizes the transition across that line, taking the pixel width into account and measures much more accurately the difference between the light and dark regions without interference from the display pixels. These are just some examples of AR/VR display evaluation, and of course there are many more that can be accomplished. The key again is to replicate the human visual experience in the headset so that the presented field of view of the display can be captured and analyzed. We'll finish up our discussion with a look at head-up displays. HUDs have similarities with augmented reality in the use of projection displays, but have unique visualization and measurement challenges as they are viewed within a vehicle cockpit. The HUD landscape is getting quite diverse, but there is a common trajectory towards augmented reality, or AR HUD, which increase the amount of useful information made available to the driver in the line of sight. Conventional HUDs, as shown on the left, project images on a single focal plane or fixed distance. These type of HUDs are still the majority systems we see in vehicles of today. To overcome the limitation of conventional HUDs, new systems are being developed which use data obtained from exterior and interior sensors. This data are then used to map projected images onto objects in the environment. On the right, this AR HUD, premiered by Panasonic at the 2021 Virtual CES show, utilizes 2D images that are mapped to external objects in 3D space. Most visual display tests remain the same regardless of the HUDs being measured, based on standards set forth by SAE for optical measurement and internal requirements. There may be emphasis on tests for certain technologies, but they all require capturing sufficient data needed to perform each of these tests, regardless of the virtual image on the projected depth. One challenge as conventional HUDs progress towards AR HUDs is the measurement system must meet new demands for image distance, resolution, and field of view. Conventional HUDs have limited projection depth, usually within a few meters. These systems typically do not require large field of view nor high resolution. AR HUD systems, on the other hand, are responsive to objects at a range of depth across a wide viewing area. These images must exhibit clarity at all these spatial points, and for this reason, resolution of the display is important as well as the focus. Here, typical differences between conventional fixed-distance HUDs and AR HUDs illustrate the challenge. The basic optical tests performed on these HUDs remain largely the same, but the focus, depth of field, resolution, and field of view becomes increasingly demanding for the measurement equipment as the display becomes more sophisticated. HUD testing requires absolute luminance and chromaticity to understand the visibility of the projection to a human operator in the wide range of environments encountered in vehicles, especially as overlaid with the external scene. A HUD optical test system is therefore based on a photopic or colorimetric system. HUD testing also involves the dimensional measurement of points within the field of view. Image-based metrology excels at this type of measurement, where distances between points in the projection can be gauged for characterizing and correcting distortion, as well as qualifying distortion, warping, and ghosting in the HUD. Using the projected image, distance, and image scaling, known points around the display can be measured and used to report various dimensional metrics. Three common dimensional measurements are distortion, warping, and ghosting. The first, a distortion test, uses a grid of points to report image centering, rotation, keystoning, and pincushion or barrel distortion. The second is a warping analysis, which would report the location of a fine grid of dots relative to the center point. The third is a ghosting analysis, which will check for dim copies of primary features and report the luminance ratio and displacement distance. Hot testing requires a comparison across the entire spatial context, with tests for contrast, uniformity, Mura, and fine defects such as particles and lines. These tests are best done with an imaging system, and since such a device can also be used for spatial contrast testing, only one device needs to be mounted into the vehicle, saving time and expense in both research and development and production environments. Electronic lenses can be paired with an imaging system to ensure focus flexibility for targeting hot projection at various distances. This is especially important for variable AR HUDs. Focus depth and aperture for these lenses are controlled via software rather than manually, eliminating human error and greatly reducing time between measurements for images at various depths. As imaging systems are pushed to focus at larger and larger distances, achieving clear images at relatively small scale requires greater image resolution. Capturing images as far as 20 meters away for AR HUDs means evaluating more visual details at more precise coordinates. Missing details will impact the qualification. An imaging system should exceed the resolution of the hot projections to ensure that the projection is evaluated in the same detail as it is produced. This is especially critical for image quality testing and can also be important for characterizing distortion, warping, ghosting, and other defects. It is necessary that the imaging system has a higher resolution and NTF to ensure that reported problems are caused by the hot system under test and not a problem with the measurement system. For hot measurements, high-resolution imaging photometers ensure repeatability, especially as the virtual image distance increases and the necessary pixel density increases. Electronic lens settings adjust quickly to various virtual image distances, allowing the capture of clear measurements of the hot projection and isolating any defect. All of these examples serve to demonstrate the need for measurement systems to continually evolve to meet new display types, integrations, and challenges. While based on a standard set of core measurement principles, display metrology is far from static. It is the innovation of display makers like all of you here that keep display metrology alive and changing. We are all excited to see the displays to come that extend metrology like this even further.
With that, we will wrap up today's course, but we would like to leave you with some thoughts to take with you through the rest of the week, and as you encounter display test projects or opportunities in the future. At the outset of measuring a display, it's important to ask yourself a few questions to guide your discussion with your internal teams and potential vendors to make sure you end up with the optimal metrological solution. Some questions are: what do you want to measure? Display output or how the display is perceived? What quantities have the greatest impact on my display performance? Are there tools designed to measure these specific quantities? Are there solutions that meet the unique requirements of my particular application? Who can I speak to about my display metrology project? Of course, we hope you will consider reaching out to our team if you have any question.
Thank you for joining this short course presentation from Instrument Systems, Konica Minolta, and Radiant Vision System. You can connect with all presenting companies and learn more about display metrology solutions at our website listed here. We appreciate your time and hope you have a great display week. On behalf of our three presenters, thank you for your time.